In the vastness of the universe, a silent drama unfolds. The Andromeda Galaxy, our cosmic neighbor, holds secrets and celestial catastrophes that shaped its destiny. Andromeda is not a simple spiral galaxy, but a colossal formation that extends over 220,000 light-years and contains 1 trillion stars. However, beneath its serene beauty lies a history marked by violent collisions and dramatic transformations. Astronomers have discovered that the double nucleus of Andromeda, a unique structural anomaly, points to ancient galactic cannibalism, when smaller galaxies were devoured to fuel its growth. In the heart of this giant, a supermassive black hole silently consumes material, affecting the fate of everything around it. Join us today on a journey through Andromeda's hidden catastrophes. We will explore its turbulent past together and analyze its future, where a cosmic event will take place that will forever change the very structure of the universe, transforming our world. At the end of the 19th century, the Andromeda Galaxy was shrouded in mystery. The first astronomers who observed it through their telescopes saw it as a blurry patch of light in the night sky. Many thought it was a nebula within our Milky Way. The first major breakthrough in understanding it came with the arrival of more powerful telescopes in 1885. From the Lick Observatory in California, they made a surprising discovery. They observed a bright new star near the nucleus of the Andromeda Galaxy, which they called S Andromeda or supernova SN 1885. It was an extraordinary event, as it was the first time that a supernova had been observed outside the Milky Way. The sudden brightness was a beacon that broke the misconceptions of that time. However, confusion arose at first. Could it be a nova, a typical phenomenon of our galaxy, or were we talking about something more substantial? The light curve of SN 1885 revealed its true nature. Unlike novae, which fade relatively quickly, the brightness of this supernova persisted for months, indicating a cataclysmic explosion, a distinctive sign that signaled the death of a massive star. Through careful analysis and advanced models, scientists reconstructed the event. They believe that SN 1885A was a Type 1A supernova, a thermonuclear explosion of a white dwarf star in a binary system. The explosion was so powerful that it temporarily eclipsed the entire Andromeda Galaxy. The observations of SN 1885 had profound implications and represented a turning point in astronomy, laying the foundations for the hypothesis that there are other galaxies composed of the same stellar phenomena as our own. The discovery paved the way for the later work of Edwin Hubble, who confirmed that Andromeda was indeed an independent galaxy and not part of the Milky Way. Today, thanks to a discovery made more than a century ago, we understand that supernovas are crucial elements in the life cycle of stars, scattering heavy elements throughout the universe and allowing us to better understand the dynamic nature of galaxies. Thus, Andromeda, which extends over 260,000 light-years, is home to a wide variety of celestial phenomena, especially in its central region and spiral arms. The central region of the galaxy is a busy hub of activity. It houses a high concentration of stars, gas, and dust. At its center is a supermassive black hole, but the region is also characterized by a prominent double nucleus, an unusual feature that distinguishes Andromeda from many other galaxies, but we will talk about it later. One of the most exciting aspects of the central region of Andromeda is the ongoing star formation, despite the presence of a supermassive black hole. The nucleus of Andromeda is a cradle of new stars. Areas of dense molecular clouds collapse under gravity, initiating nuclear fusion and giving rise to new stars. These stellar incubators are very important for understanding the life cycle of stars and the evolution of galaxies. The spiral arms of Andromeda are impressively complex. These arms are scenes of intense star formation, where young massive stars illuminate the surrounding gas clouds, creating regions known as hydrogen-2 regions. These regions are ionized by the ultraviolet radiation of the hot young stars, which makes them shine brightly. However, the spiral arms are not static, but dynamic structures influenced by gravitational interactions, and the rotational forces of the galaxy. As gas and dust move through the arms, they encounter shock waves that compress the material and trigger further star formation. This cyclical process keeps the arms alive and full of young stars. However, in the vast expanse of Andromeda, some stars play a crucial role in our understanding of the cosmos. Among them are the Cepheid variable stars, which change their brightness and provide information about stellar processes and cosmic distances. In 1923, Edwin Hubble, using the 100-inch Hooker telescope at the Mount Wilson Observatory, observed a star in Andromeda that forever changed our view of the universe. This star, later named M31V1 and known as a Cepheid variable star, plays a fundamental role in astronomy, as its predictable changes in brightness make it a reliable standard candle for measuring cosmic distances. Before Hubble's discovery, the nature of spiral nebulae, such as Andromeda, was the subject of heated debate. In 1920, Harlow Shapley and Heber Curtis debated whether these nebulae were part of our Milky Way or separate galaxies. The dispute remained unresolved until Hubble identified M31V1 as a Cepheid variable in 1923. The discovery of the relationship between the period and the luminosity by Henrietta Swan Leavitt. The relationship shows that the longer the period of variation in brightness of a nebula, the greater its intrinsic luminosity. By measuring the period and apparent magnitude of M31V1, Hubble was able to calculate its absolute magnitude and, therefore, the distance to Andromeda using the formula. Hubble determined that M31V1 was almost 1,000,000 light-years away, far beyond the Milky Way. This revolutionary discovery confirmed that Andromeda is an independent galaxy, which greatly expanded the known universe. Both amateur and professional astronomers continue to observe M31V1 and other variable stars with modern equipment. Modern CCD cameras, more sensitive than the photographic plates used by Hubble, allow even amateur astronomers to replicate Hubble's work. Variables like M31V1 remain vital tools in cosmology to this day, as they help astronomers measure distances to distant galaxies, calibrate other distance measurement methods, and refine our understanding of the scale and expansion of the universe. In addition to the variables, there are other variable stars in the spiral arms of Andromeda, including the W Ursae Majoris stars. These stars also serve as standard candles. Although they are less bright than Cepheids, their study provides additional clues about the structure and mysterious history of Andromeda. And now, something equally interesting. Our closest galactic neighbor holds secrets that have baffled astronomers for decades. Among its many mysteries, two stand out: the presence of a double nucleus and the behavior of the central supermassive black hole, detected in high-resolution images. The nucleus of Andromeda represents a unique mystery. Unlike most galaxies, which have a single central nucleus, Andromeda presents two bright nuclei. This unusual structure has led scientists to propose various theories. One of the main hypotheses suggests that the double nucleus results from the merger between a smaller galaxy and Andromeda. When a nucleus of the smaller galaxy spirals inward, two bright centers appear. The Hubble Space Telescope provided the first detailed images of this double nucleus, showing a dense cluster of stars around each. Subsequent observations from the Chandra X-ray Observatory and the Very Large Telescope expanded our knowledge, showing that one of the nuclei is probably the original nucleus of Andromeda, and the other a remnant of a captured galaxy. In the center of the galaxy is a supermassive black hole with a mass millions of times greater than our Sun. Recent research using data from NASA's Spitzer Space Telescope has shed light on the feeding habits of this colossal entity. Unlike the chaotic food consumption observed in other galaxies, Andromeda's black hole quietly feeds on streams of dust and gas that extend thousands of light-years away and continuously feed it. These spiral dust streams, similar to water drainage, maintain a continuous, smooth flow of material toward the black hole. Computer models suggest that this constant flow avoids the large luminosity fluctuations that typically characterize black holes that absorb matter in clumps. Instead, The matter forms a small disk of hot gas that gradually falls toward the black hole, keeping it relatively calm. Ongoing research, combining data from multiple telescopes and advanced simulations, continues to unravel the unique structural characteristics and enigmatic behavior of the nucleus, revealing the complex and fascinating nature of our neighboring galaxy. Andromeda has a rich and dramatic history that has shaped its current structure. Recent studies show that the formation of Andromeda was marked by significant events. First, a massive burst of star formation laid the foundation for the galaxy, followed by a second wave of star formation caused by a large wet merger, the collision of two gas-rich galaxies. Galactic archaeology has helped scientists in this task, which consists of studying ancient stars to understand the galaxy's history. By analyzing the chemical composition and movement of these stars, scientists can reconstruct the past events that shaped the galaxy. In the specific case of Andromeda, the presence of ancient stars with different chemical compositions provides clues about its turbulent past. Andromeda experienced two distinct eras of star formation. The first era was caused by a rapid accumulation of gas that resulted in a thick disk of stars. The second era, which took place between 2,000 and 4,500 million years ago, was most likely caused by a wet merger that resulted in a thinner and younger disk of stars. Over billions of years, Andromeda has grown to swallow more than 100 satellite galaxies. This process, known as galactic cannibalism, has significantly affected its structure and star formation. These interactions not only increased its mass, but also triggered new waves of star formation. One of the most dramatic events in Andromeda's history was the collision with a compact elliptical galaxy, M32. This collision profoundly affected the spiral arms and overall structure of Andromeda. The gravitational interaction caused by M32 created waves and deformations in its disk. The collision with M32 caused significant disturbances in the spiral arms of Andromeda, leading to its current structure. These interactions likely triggered bursts of star formation, creating the bright, young stars still observed in the spiral arms today. Andromeda is surrounded by numerous satellite galaxies, each of which plays a role in its evolution. In addition to M32, the second most important companion is NGC 205. Interactions with them have left remarkable traces on Andromeda, including gravitational deformations and tidal currents. However, the history of Andromeda is still unfolding, since it is on a collision course with something less abstract and more dear to us. This future collision will lead to the formation of a new galaxy that will radically change our cosmic future. In about 45 billion years, a tremendous cosmic event will occur. The Andromeda Galaxy and the Milky Way will collide. This imminent merger will forever change the structure of both galaxies, leading to the formation of a new elliptical galaxy. The Andromeda Galaxy is currently moving toward the Milky Way at about 68 miles per second. This head-on collision is an uncommon event that is affected by the gravitational attraction between the two massive bodies. Although the distances are enormous, the galaxies are destined to merge. The collision of the Milky Way with Andromeda will not be a sudden impact, but a very long process that will last several billion years. First, the galaxies will pass through each other, and their gravitational forces will create tidal distortions. As a result of this interaction, stars and gas will escape from both galaxies, forming long tidal tails. After the first pass, the galaxies will continue to interact until they eventually become a single, more stable structure. The process will lead to the formation of a new elliptical galaxy that scientists have already named Mila or Milgram. The merger will cause the dissipation of the spiral arms, transforming the galaxies into a more homogeneous, ellipsoidal shape. Although the merger will radically change the structure of galaxies, the enormous distances between stars make direct collisions unlikely. However, the solar system will be affected by new gravitational forces and could be thrown into another region of the galaxy or even expelled into space. At the time of the merger, the Sun will have become a red giant, which will make Earth uninhabitable. Long before that, The increase in the sun's luminosity, increasing luminosity of the sun, will cause radical changes on our planet, probably depriving it of its atmosphere and oceans. Therefore, with very few remains of humanity or any other life on Earth, the direct impact of the collision will be minimal. The imminent changes lead us to consider the future of humanity. As our understanding of cosmic events increases, so does our ability to adapt and explore. The merger of Andromeda and the Milky Way may inspire future generations to find new homes among the stars, advancing our journey into space, which always leads us to reflect on our place in the universe and the future of human civilization. How will we adapt to these changes? What measures can we take to ensure our survival and continue exploring the universe? As we continue to learn from the stars, we remember the incredible forces that shape our galaxy and the limitless possibilities that the future holds for us. Let's imagine a colossal object 6 million kilometers wide hurtling through space at 12 million kilometers per second toward Earth. It is not science fiction. 66 million years ago, an asteroid like that crashed into what is now the Yucatan Peninsula, forming the Chicxulub crater and triggering a mass extinction. Today, our planet continues to be threatened by near-Earth objects, including asteroids and comets whose orbits take them into our near space. NASA and other space agencies have made significant advances in tracking and understanding these potential threats, but the risk remains. Work is being done with advanced technology to monitor and mitigate these threats, from kinetic impacts to gravitational tractors. Humanity is developing strategies to protect our world from these stellar invaders. But what would happen if another asteroid the size of Chicxulub was on a collision course with Earth today? How prepared are we for such a catastrophic event? Join us to learn about planetary defense fighters. But what would happen if another asteroid the size of Chicxulub was on a collision course with Earth today? Are we prepared for such a catastrophic event? Join us to learn about planetary defense, history, science, and the future in the face of such impressive threats. 66 million years ago, an event occurred on Earth so catastrophic that it changed the course of life on the planet. The asteroid, about 6 m in diameter, crashed into the Yucatan Peninsula in present-day Mexico, forming what we know today as the Chicxulub crater. The immediate consequences were apocalyptic. The collision released energy equivalent to billions of nuclear bombs, caused forest fires and tsunamis, and launched enormous amounts of debris into the atmosphere. The most significant and lasting effect of the impact was the release of dust, soot, and sulfur aerosols into the atmosphere. These particles created a global cloud that blocked sunlight for a long period, a phenomenon known as impact winter. New research has shed light on the fundamental role of fine dust particles in this cataclysm. A study published in Nature Geoscience in October 2023 found that fine dust, particularly particles between 0.8 and 8 micrometers in diameter, played an important role in abrupt climate change. The researchers collected rock samples 66 million years old in North Dakota, a considerable distance from the impact site, containing surprising amounts of these fine dust particles. These particles remained in the atmosphere, forming a dense cloud that persisted for up to 20 years, with the first 5 to 8 years being the most severe. This long period of darkness caused a significant drop in global temperature, estimated at more than 18 degrees Fahrenheit, 10 degrees Celsius in the first year alone, as sunlight was blocked and photosynthesis stopped. Plants, unable to produce food, began to die. This collapse of plant life had a chain effect throughout the food chain. Herbivorous dinosaurs, which depended on plants for food, faced starvation. Consequently, the carnivorous dinosaurs that fed on them also died. This chain reaction led to the extinction of approximately 75% of all species on Earth. Interestingly, the new study highlights the hitherto unknown impact of dust compared to soot and sulfur, which were previously considered primarily responsible for the prolonged cooling period. The findings suggest that, while soot and sulfur blocked sunlight more effectively, the large amount and persistence of dust had a profound and lasting impact. The study also provides information on how some species manage to survive this dark period. Hibernating plants and animals had adaptations that allowed them to survive the prolonged lack of sunlight. However, the study rules out the survival mechanisms of freshwater organisms, indicating that more research is needed to fully understand the specific mechanisms of death after a Chicxulub impact. So, what are near-Earth objects in EOs? EOs are asteroids, comets, and other celestial bodies whose orbits bring them close to Earth. These objects vary in size, from small, harmless rocks to massive bodies capable of causing large-scale catastrophe. Asteroids are rocky remnants of the early solar system found primarily in the asteroid belt between Mars and Jupiter. Comets, on the other hand, originate in the outer regions of the solar system and are composed of ice dust and rocky material. As they approach the sun, they develop comas and luminous tails. The danger posed by these objects depends on their size and trajectory. Although most NEOs are too small to cause significant damage, some, like the Chicxulub impactor, could cause global catastrophes. To mitigate these risks, space agencies like NASA and the European Space Agency have developed programs to track and detect NEOs. From all over the world, constantly scan the sky and catalog the objects that approach the orbit of the Earth. One of the key instruments in this work is the Wide-Field Infrared Survey Explorer, which has been repurposed for the NEOWISE mission. Hundreds of near-Earth asteroids have been discovered and characterized by this space telescope. The role of artificial intelligence in detecting unobserved asteroids is becoming increasingly important. In May 2024, an algorithm based on artificial intelligence, known as Tracklet Less Heliocentric Orbit Recovery, or THOR, detected over 27,000 unobserved asteroids in archive images from telescopes. This artificial intelligence tool analyzes enormous amounts of data and identifies and tracks objects with great efficiency. It can process up to 1,700 million points of light in a single telescope image, connecting them into asteroid trajectories. The Verici Rubin Observatory, which will begin operating next year, will further improve our ability to detect NEOs. Equipped with advanced artificial intelligence software, such as HelioLink 3D, this observatory is expected to catalog millions of asteroids in its first months of operation, doubling the currently known population. Although no near-Earth object is large enough to destroy the planet, asteroids larger than 1.5 kilometers can cause global catastrophes. For this reason, NASA has been tasked with detecting and tracking these large objects. In 2021, NASA had detected more than 90% of the largest objects, ensuring that none of them pose an immediate threat to Earth. However, smaller objects, while not as catastrophic on a global scale, can cause significant regional damage. Take, for example, an asteroid named after the Egyptian god of chaos and destruction. This is a near-Earth asteroid that has captured the attention of scientists and the public. Discovered in 2004, this 1,000-foot wide, 304 m, asteroid initially caused concern due to calculations suggesting a possible collision with Earth in 2029. However, subsequent observations have ruled out this possibility and confirmed that Apophis will pass by our planet safely on April 13, 2029. Apophis will get incredibly close to Earth, passing within 30,000 miles, 48,800 kilometers, of our planet. 48,300 kilometers from our planet. In comparison, this distance is less than the orbits of some of our high-altitude satellites. This very close passage offers a unique opportunity for scientific observation and research. During the flyby, the asteroid will be visible to the naked eye in some regions, appearing as a moving bright spot. This exceptional event will allow scientists to study its size, shape, and composition in unprecedented detail. NASA's Goldstone Space Communications Complex in California will play a crucial role in observing Apophis using radar. Scientists hope to gather detailed information about the asteroid's surface characteristics and rotation. In addition, The NEO mission can provide additional observations focusing on the roughness and surface composition of Apophis. This data is very valuable, as it will help refine our understanding of near-Earth asteroids. NASA's OSIRIS-APEX spacecraft, formerly known as OSIRIS-REx, will approach Apophis during its closest flyby. The goal of the mission is to study the asteroid up close and provide detailed observations that ground-based telescopes cannot achieve. OSIRIS-APEX will collect data on the composition and surface structure of Apophis, as well as any changes that occur as it passes near Earth. The spacecraft's instruments will help determine the internal composition of the asteroid, which will also contribute to expanding our knowledge of the formation and evolution of the solar system. The close passage of Apophis has also attracted the attention of international space agencies. Teams from around the world plan to observe and study the asteroid using ground-based and space-based telescopes as part of the NEO project. Researchers at the Julius Maximilian University of Würzburg have proposed several concepts for small spacecraft that could accompany Apophis during its flyby. One of the proposed missions includes a small satellite that would follow Apophis for 2 months to obtain high-resolution images and measurements. Another combined concept consists of a small satellite with the European Space Agency's Ramsay mission, which would provide extensive scientific observations. Although the asteroid does not pose an immediate threat to Earth, its approach in 2029 presents a great scientific opportunity. Studying this asteroid up close will greatly improve our planetary defense strategies to protect Earth. Scientists have developed several planetary defense mechanisms, each designed to prevent potential collisions. One of the main methods is the kinetic impact strategy, which involves sending a spacecraft that will collide with an asteroid at high speed, altering its trajectory. This method is based on momentum transfer to move an asteroid to a safer orbit. NASA's 2022 mission, Double Asteroid Redirection Test, or simply DART, was the first test of this method. DART's target was a small moonlet, Dimorphos, which orbited a larger asteroid, Didymos. As a result of the collision, Dimorphos' orbit was successfully modified, providing valuable data for future missions. Another proposed method is the gravitational tractor. This method uses the gravitational pull of the spacecraft to slowly change the trajectory of the asteroid over time, maintaining a stable position near it. The gravity of the spacecraft can gradually alter the object's trajectory. Although this method is still theoretical and hasn't been tested in space, it is a promising approach to address potential threats identified in advance. In extreme cases, nuclear explosions could be used to divert or destroy an asteroid. In this approach, a nuclear device is detonated at a safe distance from the asteroid, vaporizing part of its surface and creating a recoil effect that deflects the asteroid from its path. However, this method is controversial due to the potential risks and legal implications of using nuclear weapons in space to prepare for possible asteroid impacts. International space agencies regularly conduct drills and exercises. These exercises help refine detection, tracking, and deflection strategies. Planetary defense is a global issue requiring cooperation between countries. For example, in 2021, NASA participated in an international planetary defense exercise organized by the International Asteroid Warning Network and the United Nations Office for Outer Space Affairs. The exercise simulated the detection of a fictitious asteroid on a collision course with Earth, allowing participants to practice their response strategies. As we continue to develop and refine our planetary defense strategies, international cooperation and technological advances will play a key role in protecting our world from space threats. These cooperative efforts are essential, especially as we learn more about the diverse nature of the objects that threaten us. Asteroids and comets are often considered distinct celestial bodies. Asteroids are rocky remnants of the early solar system, mostly from the belt located between Mars and Jupiter. Comets, on the other hand, are objects from the farthest reaches of our system and are composed of ice, dust, and rocky material. However, there are also rare objects that blur the boundaries between these two categories and exhibit characteristics of both. One of these objects is QN 173, discovered in 2005. This celestial body orbits like an asteroid, but behaves like a comet. Unlike ordinary asteroids, which are inert, Q173 exhibits comet-like activity, ejecting dust and developing a long, thin tail as it approaches the Sun. Q173 orbits the Sun every 5 years and spends most of its time in the outer part of the asteroid belt. However, as it approaches the Sun, it exhibits increased comet-like activity. This duality makes 2005 QN173 an interesting object for astronomers. In the summer of 2021, astronomers using the Asteroid Terrestrial Impact Alert System in Hawaii observe an object showing a comet-like tail. Subsequent observations by the L Observatory and the Zwicky Transient Facility confirmed this activity. The tail, 450,000 kilometers or 720,000 kilometers in length, suggests that the object is covered in icy material that sublimates when heated by the Sun. It is this process that converts the ice directly into gas, releasing dust and creating the characteristic tail. Interestingly, the narrowness of the tail indicates that the dust particles barely leave the nucleus at extremely slow speeds, which is a mystery to scientists, as such low speeds would not normally allow the dust to escape the asteroid's gravity. One hypothesis is that the rapid rotation of the nucleus may contribute to the dust expulsion. In addition to unique objects such as 2005 Q173, many other near-Earth objects pose a potential threat to our planet. The European Space Agency maintains a comprehensive risk list that catalogs objects with a non-zero probability of colliding with Earth. The list contains detailed information on the size, speed, and probability of collision of each object. It currently contains more than 1,600 targets. The risk list is ordered according to the Torino scale, a logarithmic scale that assesses the risk of collision based on the size, speed, and probability of collision of objects with higher values on the Torino scale. Size, speed, and probability of collision. Objects with higher values on the Torino scale pose a greater potential threat. Statistical analysis of these potentially hazardous asteroids shows that, although most NEOs pose a minimal risk, some objects require close observation. For example, the size and speed of an asteroid have a significant impact on its probability of impact and potential damage. Large asteroids, typically more than 1 kilometer in diameter, are particularly concerning due to their ability to cause global catastrophes. Fortunately, NASA and other space agencies have identified and tracked more than 90% of these large objects, ensuring that none of them pose an immediate threat to Earth. Smaller objects, while not as catastrophic, can cause significant regional damage. Events such as the Chelyabinsk meteorite in 2013 and the Tunguska event in 1908 demonstrate the potential danger of small asteroids. As we continue to discover and track NEOs and refine our planetary defense strategies, international cooperation and technological advances remain critical. By understanding the diverse nature of these celestial bodies and preparing for potential threats, we can protect our planet and ensure a safer future for generations to come. Music. Imagine a single point, just a speck of light floating in an infinite sea of darkness. It's not just a random point. It's our home, Earth. But what if we told you that this point is just a fleeting moment in a cosmic panorama so vast and complex that it defies human understanding? Imagine a night sky decorated with stars, each representing a sun, many of which have their own planets. Now, multiply that image by 100 billion. Even then, we would barely scratch the surface. Beyond our Earth, beyond our sun, even beyond our galaxy, lies a structure so vast that everything you know seems like a thread in an unfathomable cosmic web. The human mind, itself a marvel, struggles to comprehend this scale. Our brains are built to understand the elevations and slopes of mountains and the immensity of oceans. But how can we understand a structure that spans billions of light years? Today we are on a journey to explore these galactic threads, the sinuses and muscles of the universe itself. We will delve into an almost incomprehensible realm, where even light's speed seems slow. Spiders weave intricate webs, fine but strong, each thread connected to others in a complex pattern. The architects of nature create these webs to survive, to capture prey, and probe the environment. Now imagine a web woven not by spiders, but by the very fabric of space-time, a web that connects galaxies, star clusters, and dark matter in a complex network. This is the cosmic web, the grand architecture of our universe. Each node you see here is not a single star or planet, but an entire galaxy, a colossal cluster of billions of stars, planets, and other celestial objects bound by gravity. But what gives this network its structure? The answer lies in something we cannot even see: dark matter, which scientists believe makes up about 27% of the universe. Dark matter acts as the framework on which this network is built. Although it is invisible, its presence we cannot even see. Dark matter. Dark matter, which scientists say makes up about 27% of the universe, acts as the framework on which this network is built. Although it is invisible, its presence is perceived through the gravitational pull that determines the formation of galaxies and the trajectories they follow. The cosmic web has not always been as we see it today, but has evolved over billions of years, beginning with small density fluctuations in the early universe. These fluctuations grew, attracted by gravity, and eventually formed the majestic filaments and nodes we see now. One of the most impressive examples of a galactic filament is the Great Wall of Hercules in the Corona Borealis. This colossal structure extends for 23 billion light-years, making it one of the largest known structures in the universe. Understanding this network is not just an academic exercise. It is a quest to understand our place in the universe. Are we simply an accidental byproduct of cosmic evolution, or is there a grander design at work? Scientists use a variety of tools to study this network, from telescopes that can see distant galaxies to simulations that model dark matter's behavior. Each discovery is a piece of the puzzle, a thread of a story that spans the entire universe. Here is the Earth, a blue and green pearl suspended in the immensity of space, a planet teeming with life, from the microscopic to the magnificent. It is easy to think of Earth as the center of everything, but in the grand scheme of the universe, it is just a speck within our solar system. Earth is just one of 8 planets orbiting the Sun, and yet it stands out for its unique ability to harbor life. The oceans, the atmosphere, the magnetic field. All these elements are in delicate balance. If we zoom out even further, our entire solar system becomes a small point in one of the spiral arms of the Milky Way, a galaxy that is home to hundreds of billions of stars, each of which could contain its own planetary system. And the Milky Way is just one galaxy in a cosmic network of hundreds of billions of galaxies. Each of these galaxies is a node, a focal point in this unimaginable structure. Even within our galaxy, Earth is influenced by forces beyond its control. Dark matter, the invisible backbone of the cosmic web, shapes the structure of the galaxy and, as a result, the environment around Earth. However, despite its apparent insignificance in the cosmos, Earth is unusual for one reason: it has life. It is the only known celestial body where life not only originated, but has evolved to an incredible level of diversity and complexity. Humanity's quest to understand its place in the universe has led to remarkable scientific advances. Telescopes observe the most remote corners of the universe, and supercomputers simulate the cosmic web, helping answer fundamental questions about the nature of reality. For example, look at the sun, that ball of burning plasma that illuminates our sky and heats our planet. It is the reason why you can see these images, the reason why life exists on Earth. But in the context of the cosmic web, the sun is just a node, a solitary star among countless others. Near the sun we find other stars, some smaller and colder, others larger and hotter. Each of these stars is like a bead on a huge cosmic thread joined by gravity and dark matter. Our sun is located in the Orion arm of the Milky Way, a small spiral arm located about 27,000 light-years from the galaxy's center. Even within our galaxy, It is nothing special, just one of the approximately 400 billion stars in the vast expanse of the cosmic web. Stars like our Sun form complex nodes that connect larger structures, such as galaxies and galaxy clusters. They are the building blocks, the fundamental units that shape the network. So what powers this celestial beacon? The answer is nuclear fusion. In the depths of the Sun, hydrogen atoms collide and fuse to form helium, releasing enormous amounts of energy. This energy not only powers the Sun, but also balances the gravitational forces that try to compress it. This energy has far-reaching consequences. It provides Earth with the heat and light necessary for life, drives our climate systems, powers photosynthesis, and even influences Earth's climate in the long term. Understanding the Sun is fundamental to understanding the cosmic web. Several missions have been launched, such as the Parker Solar Probe and the Solar Dynamics Observatory, to study the Sun's behavior. These missions provide information on solar cycles, magnetic fields, and even the Sun's future. Although the Sun is a vital node in the cosmic web, which nurtures life on Earth and influences our local space environment, it is just one example in a universe teeming with stellar diversity. Each star, regardless of its size or lifespan, plays a role in shaping the cosmic web. From the smallest red dwarfs to massive blue giants, each star is a unique node that contributes to the overall structure of galactic filaments. Stars are often classified by mass and brightness, represented on a chart known as the Hertzsprung-Russell diagram. This diagram shows a star's life stage and gives clues about its future destiny. Let's take, for example, a red dwarf, the most common star type in the universe. Small, cold stars, also called M-type stars, often have less than half the mass of our Sun. They compensate for their small size with longevity, as they burn for tens or hundreds of billions of years. Red dwarfs are frugal. They convert hydrogen to helium much more slowly than larger stars. This slow lifestyle allows them to be among the longest-lived objects in space. Now let's compare that to O-type stars, the rare titans of the stellar world. These stars are over 15 times more massive than the Sun and can be a million times brighter, but they live fast and die young, often in spectacular supernova explosions. Type O stars end their lives dramatically. They collapse under their own gravity, then explode as supernovas. These explosions scatter elements like carbon, oxygen, and iron into space, which favors the formation of new stars and planets. Star clusters are like cosmic nurseries, places where different types of stars are born. These clusters serve as nodes in the cosmic web, joining different regions of the galaxy and even connecting galaxies to each other via filaments. Computer simulations help astronomers understand how different star types contribute to the cosmic web. These virtual models can simulate billions of years of cosmic evolution in weeks, showing how stars serve as building blocks of larger cosmic structures. Thus, we have discovered that stars are not eternal. They're born, live, and eventually die. The life cycle of a star is a cosmic journey that spans billions of years, playing a key role in the evolution of the universe and the structure of the cosmic web. The birth of a star is a spectacle of cosmic proportions. It begins in a nebula, a vast cloud of gas and dust. Gravity attracts these particles, which become denser and hotter until nuclear fusion ignites a new star. Once a star reaches the main sequence, it enters a period of relative stability. The hydrogen in its core converts into helium, releasing energy that balances the gravitational forces that try to compress the star. This is the longest phase of a star's life, where our Sun is now. But even stars like ours must face changes. In about 5 billion years, the Sun will run out of hydrogen. Its core will contract, but its outer layers will expand, turning it into a red giant. This phase is the prelude to the star's final destiny. Depending on its mass, a star will have one of several endings. Stars with less mass, like our Sun, will lose their outer layers, leaving a white dwarf behind. More massive stars can undergo a supernova explosion, resulting in a neutron star or black hole. These deaths are not in vain. The agony of stars scatters important elements through space, elements that will become building blocks of new stars, planets, and even life. Thus, the life and death of stars are an integral part of cosmic creation and destruction. The cosmic web, from stars to entire galaxies, is a complex network of interconnected structures. But what unites these galaxies? What are the threads that weave the universe's complex fabric? The answer lies in the galactic clusters. Galactic clusters are huge collections of galaxies held together by gravitational force. They can contain a few or thousands of galaxies and often span millions of light years. Just as dark matter plays a role in individual galaxies, it also acts as an invisible glue in galactic clusters, even though we cannot see it. Though we cannot see it, we know it exists, as it holds the cluster together and shapes its overall structure. Within a cluster, galaxies are not static, but in constant motion. Some of them may be heading toward the center of the cluster, while others may be on their way to its edge under the influence of complex gravitational interactions. Sometimes these interactions can lead to dramatic events, such as galactic collisions. When galaxies collide, their stars, gas, and dark matter merge to form a new, larger galaxy. These events are crucial for the evolution of galactic clusters and, by extension, the cosmic web. But clusters are not the end of the story, as they often group together to form superclusters, among the largest known structures in the universe. These superclusters serve as main nodes of the cosmic web, uniting numerous clusters and filaments. Understanding galactic clusters is key to unraveling the mysteries of the cosmic web, as they serve as threads connecting galaxies, forming paths through which matter and energy flow on a cosmic scale. Having studied the colossal structures of galactic clusters, the threads that weave the cosmic web, we now turn our attention to an even more mysterious phenomenon. What if there were real threads, chains of pure energy binding the universe's fabric? These hypothetical one-dimensional defects in space-time could be the universe's loose threads, remnants of the earliest moments after the Big Bang. Let's imagine the universe moments after the Big Bang, in a hot, dense state of pure energy. As the universe cooled and expanded, this energy condensed into matter and structure. However, not everything went well. In some regions, twists occurred that led to the formation of cosmic strings. Cosmic strings, if they existed, would be unimaginably thin but incredibly dense. A string less than an inch wide could weigh as much as Earth. They would extend along the vast expanse of the universe, perhaps even from one end to another. Due to their enormous mass, cosmic strings would exert a strong gravitational pull that would affect the movement of galaxies and even bend light. They could serve as cosmic highways that direct the flow of matter and energy throughout the universe. The search for cosmic strings continues. Scientists are using a combination of theoretical physics and observational astronomy to search for these elusive structures. If the existence of the strings is confirmed, they could become the missing links that help us understand not only how the universe is organized, but also why it is organized this way. However, let's go back to the structures of incommensurable scale, the superclusters. They are the gravitational anchors that hold together vast networks of galaxies and galactic clusters. Let's imagine that we move away from our galaxy, the Milky Way, beyond our local group of galaxies, and even beyond our local Virgo supercluster. We would find a network of superclusters, each containing hundreds or thousands of individual galaxies united in a complex gravitational dance. Superclusters are unevenly distributed, forming a kind of cosmic skeleton around which galaxies and clusters of galaxies are located. This skeleton gives the cosmic network the shape that defines the large-scale structure of the universe. Within superclusters, galaxies and clusters are in constant motion under the influence of the collective gravitational attraction of the entire structure. This dynamic flow of matter and energy is what keeps the cosmic network alive and constantly changing. Among the most intriguing aspects of superclusters is the presence of gravitational anomalies, such as the Great Attractor. These are regions with such a strong gravitational force that they influence the movement of the entire supercluster, acting as axes of the cosmic network. Understanding superclusters is fundamental to cosmology, as they constitute the largest laboratories for studying the expansion of the universe, the distribution of dark matter, and even the mysterious force of dark energy. Scientists estimate the observable universe at 2 trillion galaxies, and yet what we can see represents less than 5% of the universe. At the edge of cosmic knowledge, we feel humbled by the scale and complexity of the universe, from the smallest particles to the largest galactic filaments. Each element is a piece of the puzzle. Here we are, a pale blue dot, a mere speck in the cosmic network. But it is from this vantage point that we have begun to unravel the deepest mysteries of the universe. Armed with telescopes capable of seeing billions of light years away, we become not only spectators, but active participants in this cosmic journey, and each new discovery is a step towards answering the eternal question that leads us all to reflect. What other mysteries does the universe hide that we have not yet unraveled? The solar system has served as a reliable laboratory for life, but one day humanity will have to abandon its native Earth to continue to exist. In recent decades, scientists have been desperately searching the dark depths of space for a refuge for life. So far, none of the exoplanets we have found have refuted the hypothesis of the singularity of life. But what if we are simply looking in the wrong place? Perhaps it is not the planets that contain all the answers, but their exomoons of the mystical deep space are different from any other satellite in the solar system. The size of our Earth, these hidden giants have an amazing characteristic. Inside them, life can be found many more times than on normal exoplanets. Today, we will immerse ourselves in the mysterious distant universe and try to discover why exomoons could one day change humanity. Let's go back to the beginning of exoplanet science, since astronomy received a strong boost only in the mid-20th century. Scientists began studying the first exoplanets not long ago. The first confirmed exoplanets were recorded in 1992. It was a group of planets with mass similar to that of Earth orbiting the pulsar PSR B1 1257+2. Only 3 years later, scientists found the first planet orbiting the star 51 Pegasi, similar to our Sun. This was the birth of exoplanetary science, dedicated to the study of planetary systems outside our solar system, and, in addition, to the search for places where life similar to human life could originate. They did not have to wait long. In the following years, astronomers found several more exoplanets, until in 2009 the Kepler Space Telescope was sent to explore outer space. In just 5 years of operation, it was able to confirm about 715 exoplanets with a size and conditions similar to those of Earth. Currently, we already know more than 5,500 planets outside the solar system, and it is likely that the recently sent James Webb Telescope can show us even more distant planets. In 2013, scientists were able to determine the color of the planets for the first time, and a year later, they were able to record the magnetic field and, subsequently, volcanic activity. Finally, in 2018, astronomers made a new potentially revolutionary discovery. For the first time, a possible exomoon was recorded near the planet Kepler 1625b. Although this may not seem like such an incredible discovery at first, exomoons open a new chapter in modern astronomy. They are not only novel and unexplored space objects so far, but also near the planet Kepler 1625b. Although at first glance this may not seem like such an incredible discovery, exomoons open a new chapter in modern astronomy, not only because they are novel and so far unexplored space objects, but also because they are potential elements to sustain life on exoplanets and on the satellites themselves. Each year, knowledge about distant and faint exoplanets deepens, bringing scientists closer to a complete picture of the history of the entire universe. But how did scientists manage to confirm so many planets in such a short time, when it is impossible to take a picture of each one? Only 69 planets have been found with images. The most popular method is the transit method, which you may already know. When an exoplanet passes in front of its central star, it becomes slightly fainter revealing the presence of an object orbiting around it. Although this method does not allow direct observation of the planet and may turn out to be just an error, it is currently the most effective of all. The exploration of exoplanets plays a crucial role in all of astronomy and in the future of all humanity. Exomoons, as a new chapter in exoplanet science, may have great potential for the search for extraterrestrial life. However, despite this, exomoons are not of great interest for current research now. The main problem with the search for these exoplanets is the difficulty in detecting them with telescope radars. Although no scientist denies that some exoplanets may have satellites, it is an extremely difficult task and even to some extent impossible for our current technologies. The transit method, or more precisely the method of studying the displacement of the spectrum of stars, can confirm the existence of an exoplanet, but not that of a satellite that orbits around it in almost no circumstance, unless, for example, the spacecraft is in the closest possible proximity to the object of observation due to an insignificant change in the brightness of the star. Therefore, even the first exomoon found by Kepler, and those discovered later near the planets Kepler 1708b and Kepler 1513b, are still not considered conclusive proof of their existence, and, therefore, there is the possibility that it is simply some kind of technical error during the observation, which is not so far-fetched, since subsequent observations did not yield encouraging results. However, as in the case of the giant satellite Kepler 1625b, an exomoon can be detected if it is large enough. So far, the first hypothetical exomoon could be the size of the Earth and have a strange inclined orbit, like Neptune's moon Triton. Such a huge size for a possible moon could become one of the most important elements in the search for other moons. Therefore, more than 20 exomoon candidates are currently known, all of them gigantic, probably at least for Kepler 1625b, the star around which it orbits being a red giant. This dying star can heat the moon's atmosphere, which would increase its effective diameter and allow scientists to detect satellites more frequently. However, perhaps exomoons do not have too much scientific importance at this time for scientists to invest many resources in developing technologies to find them at this stage of our science. Exomoons do not appear to have a higher priority than other space objects, such as exoplanets themselves. The satellites of distant planets are too complex to study and have many possibilities of giving false positive results. So months or even years of observation and analysis may be necessary to confirm the existence of a satellite, when it seems more rational to dedicate those resources to exploring a planet with the potential to harbor life, including human life. Of course, it is possible that exomoons hide life inside, but alternatives in the form of rocky exoplanets like Earth are still much more important in scientific circles. So let's focus on the moons themselves and try to investigate them. Is it really necessary to study these mysterious, hidden moons? In fact, these moons contain a lot of information for our complete understanding of the structure of the universe. But this will only be possible in the future, although not in the near future. The first thing that catches the attention of scientists, even of simple exomoon candidates, is their size. The largest moon in the solar system, Ganymede, which orbits around Jupiter, has a DI of 3,273 miles, or 5,268 kilometers, but the recorded exomoons can reach the size of the Earth or even Neptune. Therefore, since these moons are even difficult to distinguish from exoplanets, it is incredibly exciting to imagine what these moons could be like and what activity they could present. It is possible that some large exomoons have many planetary characteristics, and that their study could change everything we know about satellites. Their similarities with other exoplanets, such as their probable geological activity, lead us to the next important point for careful study in the future: the support of life. We know that several moons of the solar system, such as Enceladus or Europa, despite their low surface temperatures and small size, could hypothetically be a refuge for living organisms due to the presence of global oceans. However, what about much more massive moons that can not only support a dense atmosphere, but also have more access to the chemical elements needed for construction? both from the inside and from the outside. According to a study by the University of Washington, exomoons have more potential to harbor life than even exoplanets, since they also have a habitable zone, although is slightly different. But the main argument in favor of exomoons is that one of the most intriguing places for the existence of life is the availability of various heat sources. The first source is the star itself, and the second is its planet. The moons are heated by the gravitational attraction of the planet, which keeps the probable water inside the moon in a liquid state. In addition, the heat of an exoplanet can stimulate geological activity, such as volcanic eruptions, creating enough gas inside the moon to maintain an atmosphere for a long time and also bring to the surface various crucial chemical elements. So exomoons are not as simple as they seem. Perhaps the difficulty of finding them will be rewarded with a potential advance for science. Finally, exomoons can become the necessary tool to study the formation of our universe. Since the analysis of exomoons near different stars and planets can reveal to scientists how space objects are formed, what factors are responsible for sustaining life, and what is the history of other planetary systems in general. In particular, comparing the moons of the solar system with those of distant systems can provide scientists with an understanding of the particularities and conditions of their development, as well as an approximate value of the abundance of systems in which complex intelligent life has developed. The Earth, hypothetically, could be almost the only planet in which life could have formed, at least in the visible universe. And any clue about exomoons with potentially greater possibilities of harboring living organisms could confirm or deny this hypothesis. However, for now, the in-depth exploration of exomoons is only a matter for the future. On the other hand, the James Webb Space Telescope mission will continue for several more years, so perhaps the hope of finding an exomoon for the first time this decade will not disappear. However, since the search for exomoons is an extremely difficult and almost impossible task for our current technologies, it is likely that exomoons will become one of the engines of technological progress, since we know that the transit method or the gravitational lens will not help to search for microsignals of the presence of exomoons. So this factor already poses a challenge for scientists, who must modify or even create new technologies to capture such subtle objects. However, this is a task for the near future now. In the long term, both the intriguing moons and the exoplanets will require a much more exhaustive analysis, including the use of images and samples of the atmosphere or even the soil. So, if interesting candidates are ever found where extraterrestrial life exists, it is likely that exhaustive space missions will be carried out that will advance human knowledge in this field. The only step we have left to take is to find such an exoplanet or exomoon. In 2026, the European Space Agency plans to send the Platon mission, which will continuously observe several areas of outer space to capture objects in transit. The mission will last 6 years and could be the one that achieves this expected discovery. However, the benefits of the search and exploration of exomoons are not limited to technological advances. Exomoons are very valuable natural laboratories located near various planets and stars, and the analysis of the impact of these bodies on the moons will not only deepen what is known about the formation of planets, but will also demonstrate to scientists the variety of conditions in which life can develop. For example, traces of biomes or even technological footprints created by civilizations on various moons can provide a clear picture of the indications of the development of intelligent life, which would allow establishing more priority routes for future missions to the planets or moons with the highest probability of harboring extraterrestrial life. But for now, we can only wait for the moment when we find the first exomoon and begin a long but exciting journey that will change scientific and technological life. Exomoons, despite their invisibility and skeptical insignificance, may one day crucially change everything that the human race knows about our vast universe. Even a small observation can end up becoming the main engine for revolutionary discoveries. Continued research will reveal more and more answers, and only by pursuing this knowledge will the mysterious and cumbersome cosmos one day cease to be so confusing for us. But given the immensity of the universe, we must never lose our enthusiasm for learning no matter how difficult and distant our results may be. Let us imagine a colossal, invisible force controlling the galaxy's existence. This hidden director is none other than a supermassive black hole. Although often described as chaotic monsters that consume everything, these giants play a key role in the life cycle of galaxies. In the center of most large galaxies lies a supermassive black hole whose gravitational force is so strong that not even light can escape it. However, they actually do more than absorb matter. They act as the heart and lungs of their galaxies, giving life to the celestial environment in ways we're just beginning to understand. Recent research shows that the jets of gas and radiation expelled by the poles of supermassive black holes are similar to the airways that feed our lungs. These jets create shock waves that oscillate in a manner very similar to the thoracic diaphragm of our chest cavity, which moves to inflate and deflate lungs. This respiratory system helps regulate the growth of galaxies, preventing them from becoming too large and ensuring a delicate balance in the cosmic ecosystem. A simulation shows how the heart and lungs of a galaxy, in the form of gas columns coming from a central supermassive black hole, can prolong its life. If these supermassive black holes did not act as galactic regulators, the universe would be full in the form of columns of gas coming from a central supermassive black hole can prolong its life. If these supermassive black holes did not act as galactic regulators, the universe would be full of zombie galaxies, enormous clusters of dead or dying stars. The shock waves generated by the jets of black holes can prevent star formation by heating the surrounding gas and preventing it from cooling and condensing to form new stars. This process may seem destructive, but it is necessary to maintain the health and longevity of galaxies. Today we will try to understand the mysterious nature of supermassive black holes, learn the profound impact they have on the universe, and, in the end, realize that even in the darkest corners of the cosmos, there is a heartbeat connecting us all. To fully understand the impact of black holes on galaxies, we need to understand their formation, their types, and some key discoveries. Black holes can form in two main ways. The most common is associated with the death of massive stars. When a star with a mass between 8 and 10 times that of our Sun exhausts its nuclear fuel, a catastrophic explosion known as a supernova occurs. The core collapses under its own gravity, forming a stellar black hole. These black holes usually have a mass several times greater than that of the Sun. Another way is the direct collapse of massive gas clouds, which completely omits the stage of star formation. This process can lead to the formation of black holes with masses ranging from thousands to hundreds of thousands of solar masses. These direct collapses are believed to have occurred in the early universe and were the origin of the supermassive black holes we see today. The concept of a black hole was first predicted by Carl Schwarzschild in 1915 as an exact solution to the equations of general relativity. These equations describe how matter forms the fabric of space and time. The Schwarzschild solution allowed us to discover regions where gravity is so strong that nothing, not even light, can escape from it. The first black hole confirmed by observations was Sagittarius X1, discovered in 1964. This stellar mass black hole in the Milky Way was identified by the emission of X-rays caused by the accretion of material from a companion star. This discovery was the first convincing proof that black holes are not just theoretical constructs, but real objects in the universe. Scientists have determined that a black hole consists of three main regions: the event horizon, the photon sphere, and the singularity. The event horizon is the limit beyond which nothing can pass. Once inside its limits, the photon sphere is a region where gravity is so strong that light particles are forced to orbit the center. There is a singularity there, a point of infinite density where the laws of physics, as we know them, break down. Black holes come in a wide variety of sizes. Stellar mass black holes form from the collapse of stars and have masses several times greater than that of the Sun. Supermassive black holes, located in the center of most galaxies, have masses ranging from millions to billions of solar masses. Intermediate mass black holes, less common, fall between these two categories and have masses between 100 and 100,000 solar masses. The 2019 Event Horizon Telescope collaboration captured the first image of a black hole located in the M87 galaxy. In this historic image, the shadow of the black hole can be seen against a bright accretion disk. The observation provided direct visual confirmation of theories about black holes and opened up new possibilities for studying these mysterious objects. One of the most common and debated questions lately about black holes is whether they die. According to Stephen Hawking's theory, black holes can slowly evaporate over time through a process known as Hawking radiation. This occurs when pairs of virtual particles form near the event horizon. One falls into the black hole, and the other flies away for an incredibly long period. This trick of ejected particles can cause the black hole to lose mass and eventually vaporize. Although black holes are depicted in science fiction, they are not cosmic vacuum cleaners that indiscriminately absorb everything around them to hit them. Objects must get incredibly close to the event horizon. Furthermore, although it has been proposed that black holes are possible wormholes or portals to other universes, these ideas remain speculative and are not supported by any observational data. Scientists estimate that the Milky Way alone contains more than 100 million black holes. Understanding the fundamentals of black holes, how they form, their different types, and key discoveries lays a solid foundation for studying their profound impact on galaxies and the entire universe. So, although supermassive black holes are invisible, their presence is noticeable due to the enormous gravitational forces they exert on their environment. But how do these colossal formations arise, and what are their defining characteristics? In theory, a black hole forms when a significant amount of matter is compressed into an incredibly small space, creating a gravitational field so powerful that nothing can escape. This concept, once considered too fanciful to be real, is now an accepted reality. Black holes, especially supermassive ones, are scattered throughout the universe, and their number may amount to billions. The supermassive ones, with masses millions or billions of times greater than the Sun, are detected thanks to their gravitational influence on nearby stars. These stars orbit the black hole much faster than they would around a normal object of similar mass. By measuring these orbital speeds, astronomers can estimate the black hole's mass. For example, the black hole located in the center of our Via Láctea, Sagittario, has a mass of about 4 million solar masses. Some supermassive black holes even surpass Sagittarius A. The dwarf galaxy Leo 1 houses a black hole with a mass of about 3 million solar masses. In the neighboring elliptical galaxy Centaurus A, there is another black hole with an astonishing mass of 55 million solar masses. Even more colossal is a black hole in the galaxy cluster AL 2261, whose mass is estimated at about 100 billion solar masses. Although its exact location remains unspecified, these black holes, especially in an active galaxy, behave differently, surrounded by an accretion disk of gas and dust that rotates rapidly and can emit enormous amounts of energy, sometimes eclipsing their entire galaxy. This same process was captured spectacularly by the Event Horizon Telescope in 2019, when it photographed the accretion disk around the supermassive black hole of Messier 87, revealing the ominous shadow of a black hole with a mass of 65 billion solar masses. The formation of these supermassive black holes is subject to intense study and speculation. Unlike the vacuum cleaners of science fiction, real black holes attract matter by gravity rather than by active suction. This gravitational attraction becomes unusually strong at short distances, but at greater distances, it behaves like the attraction of any other object of similar mass. According to one theory, the oldest supermassive black holes formed almost immediately by the gravitational collapse of massive gas clouds containing as much matter as millions of stars. This direct collapse model suggests that these black holes could have formed in as little as 150 million years, a blink of an eye by cosmic standards. According to another hypothesis, primordial black holes, born in the extreme conditions of the Big Bang, served as seeds for later growth. By studying these colossal formations, we obtain information about the fundamental processes that shape galaxies and, by extension, the universe itself. But what happens when two galaxies collide? It is not just a dramatic cosmic event. It is a transformative process that changes the very structure of the universe. At the center of these galactic collisions are the supermassive black holes, and their interactions produce some of the most energetic phenomena known. When galaxies approach each other, their central supermassive black holes begin to interact gravitationally, spiraling toward an inevitable merger. This process is not silent, but sets in motion enormous amounts of ambient gas and dust, creating a turbulent environment conducive to extraordinary phenomena. Physicists have modeled these colossal mergers and discovered that, as black holes spiral closer, they can produce jets of incredibly energetic electromagnetic radiation that shoot out along the axis of rotation, with much more power than normally observed around isolated black holes. The cosmic spectacle begins even before the black holes completely merge, offering astronomers a possible warning of these events. When these supermassive black holes finally collide, their jets combine into a single burst of high energy that can be accompanied by less directional bursts, increasing the chances of detection. The fusion process sets the surrounding plasma in motion, causing powerful jets that, in theory, can be observed billions of light years away. The detection of these cosmic events is not only exciting, but offers a unique opportunity to test the limits of Einstein's general theory of relativity under extreme conditions. The observation of these mergers can reinforce the current understanding of gravity or open new avenues in physics that could lead to alternative theories. Future missions, such as the Space Antenna with Laser Interferometer, or simply LISA, promise to expand our ability to locate these mergers. LISA, a joint project of NASA and the European Space Agency, will orbit the Sun and detect the gravitational waves emitted by these mergers. The combination of gravitational wave data with electromagnetic observations will allow us to precisely locate and study these mergers. Until these advanced instruments come into operation, astronomers depend on existing observatories to detect electromagnetic jets, which provide a dynamic vision of the evolution of galaxies and demonstrate how these mergers can drastically change their structure and behavior. But let's take a closer look at Sagittarius A, which has 43 million times the mass of the Sun. In mid-spring this year, the giant of our galaxy revealed new secrets thanks to advanced observations from the Event Horizon Telescope. For the first time, astronomers have recorded polarized light around Sagittarius A, providing new insights into the magnetic fields surrounding this black hole. Polarized light is crucial to understanding these fields, as it shows how light waves are oriented and allows us to understand the properties of the gas and the mechanisms that drive the black hole. Interestingly, the magnetic fields around Sagittarius A are surprisingly similar to those observed around the much larger black hole in the galaxy Messier 87, which has a mass 65 billion times that of our Sun. This similarity suggests that strong and organized magnetic fields may be a common feature of all black holes, regardless of their size. The presence of such magnetic fields makes intriguing the possibility that Sagittarius A may contain a hidden jet. In other black holes, these fields drive powerful currents of matter, although Sagittarius A appears relatively calm and consumes a minimal amount of matter. The similar structure of its magnetic field suggests the possibility of a weak jet that has not yet been observed. This new image of the black hole in the center of the Via Láctea tells us that there are strong, ordered, and swirling magnetic fields near the black hole, explains Sarah Issoun, co-director of the study and fellow of the Einstein program of NASA's Hubble program at the Center for Astrophysics of Harvard and Smithsonian. These fields are crucial to how black holes interact with the gas and matter around them. It was the EHD, a set of telescopes from around the world, that made these revolutionary observations possible by combining data from multiple telescopes. The EHD forms a virtual telescope the size of the Earth, capable of capturing unprecedented details of black holes. Although Sagittarius A is closer, it presents a unique challenge due to its smaller size. The material that rotates around it moves quickly, making it difficult to obtain sharp images. In contrast, in the large M87, the material moves more slowly, making it easier to observe. Overcoming these difficulties has provided invaluable data to compare black holes at opposite ends of the mass spectrum. The similarity observed in the magnetic fields between Sagittarius A and Messier 87 suggests that our galaxy's central black hole may have a hidden jet. If it existed, it would provide new knowledge about the behavior and the evolution of the black holes and the galaxies in which they are located. The observation of this jet would be a great discovery, linking Sagittarius A with the energetic processes that shape galaxies. The discovery of this jet would greatly expand our understanding of how black holes affect their environments. The jets can expel gas and dust, affecting star formation and the general evolution of galaxies. When comparing different black holes, the astronomers will be able to identify the universal principles that govern these mysterious objects. The study of our own supermassive black hole allows us to ground these abstract concepts in a familiar context, bringing distant space closer to home. The influence of supermassive black holes extends far beyond their gravitational effects. The relativistic jets can have a dramatic effect on the formation and evolution of the galaxies, affecting everything from the formation of stars to the distribution of the gas and the dust. A striking example of the influence of the jets of black holes is the Taza Date galaxy, located at a distance of about 1,300 million light-years from the Earth. The Taza Date galaxy owes its name to its peculiar handle-shaped structure, which was formed due to the activity of a relativistic jet coming from its central supermassive black hole. This galaxy is a clear example of how even the low-power jets can significantly affect the environment, even in the case of the radio-silent galaxies. The jets can redistribute and disturb the surrounding gas, which will have an impact on the capacity of the galaxy. Recent observations with the Great Acoma Millimeter Set have shown that the jets of the Kuiper galaxy, although relatively weak, move heat and accelerate the gas of the galaxy, even in the case of radio-silent galaxies. The jets can redistribute and disturb the surrounding gas, which affects the galaxy's capacity to form new stars, explains Christina Rouse-Alida, astronomer at the Institute of Astrophysics of the University of California in Santa Cruz. The effects of these jets do not always occur head-on. The study discovered that the most significant effects in the Taza Date galaxy occur perpendicularly to the direction of the jets. This lateral turbulence is caused by shock waves generated by the jet bubble, which heats and inflates the gas. These interactions can prevent the formation of stars by preventing the gas from cooling and collapsing to form new stars, while the strong jets can heat the gas of the galaxies to such a point that they slow down their growth, preventing the formation of new stars. Weaker jets, like those of radio-silent galaxies, also play an important role. These jets can stir a galaxy's gas, causing its movement and redistribution. This activity can give rise to new structures inside the galaxy and affect its long-term evolution. Understanding the influence of these jets allows the astronomers to reconstruct the complex puzzle of the formation of the galaxies. The supermassive black holes are an integral part of the life cycle of the galaxies, from the dramatic changes caused by the powerful jets to the more subtle but significant effects of the weak ones. Stay tuned as we explore together the forces that shape our universe. In the midst of the peace and tranquility of the celestial bodies of the solar system, there is an object that greatly disturbs the peace of the rest, the Io moon. Unlike any other moon orbiting mighty Jupiter, Io is shrouded in mystery, a world of fire and fury, a stark contrast to the icy moons and calm planets that share its cosmic neighborhood. This mysterious moon, the most volcanically active body in our solar system, is a testament to the dynamic forces at play in the cosmos. Its surface, plagued with hundreds of active volcanoes, tells the story of the relentless and complex gravitational pull of Jupiter and other moons. Meet Juno, NASA's intrepid explorer, on a journey to this fiery world. Its mission is to unravel the mysteries of Io, capture its burning essence, and discover the secrets that for so long have remained hidden under its tumultuous surface. As Juno gets closer than it has in 2 decades, we stand on the threshold of new discoveries, ready to unravel the mysteries of this volcanic moon. What will Juno tell us about Io's turbulent volcanoes? How does this moon's turbulent nature affect giant Jupiter and its other moons? And what can Io tell us about the forces that shape our solar system? Let's find out. Discovering new views of space. Juno, a spacecraft made not only of metal and circuits, but also of ambition and curiosity, embarks on a journey that has not been carried out in more than 2 decades. For the first time in 20 years, a spacecraft dares to get so close to Io that we will be able to see up close a world of extreme volcanism. Juno's approach is not just a routine flyby, but an audacious immersion into the unknown. The spacecraft, equipped with state-of-the-art instruments, is designed to withstand the harsh radiation environment of Jupiter and its moons while approaching the rugged surface of Io at a distance of 930 miles. Juno's sensors come to life, taking high-resolution images and compiling valuable data. At the end of 2023, the probe made its closest flyby, capturing some incredible images in the process. In them, Jupiter's moon seems to shine with sulfuric tones, and its surface is dotted with spots created by the volcanic activity that lashes it. Combining the data of this overflight with our previous observations, the scientific team of Juno is studying how the volcanoes of Io vary, according to the astronomer Scott Bolton of the Southwest Research Institute. We're looking for the frequency with which they erupt, their brightness, and their temperature, how the shape of the lava flow changes, and how Io's activity is related to the flow of charged ions. The volcanoes of Io vary, affirms astronomer Scott Bolton of the Southwest Research Institute. We're looking for the frequency with which they erupt, their brightness and temperature, how the shape of the lava flow changes, and how the activity of Io is related to the flow of charged particles in the magnetosphere of Jupiter. The heart of this mission lies in the technological skill that Juno possesses. The JunoCam camera of the spacecraft continues taking spectacular images despite the challenges posed by the intense radiation of Jupiter. The Stellar Navigation Camera, which is also a scientific instrument, provides the highest resolution images of the surface of Io obtained to date on Earth. Scientists are studying the data arriving from Juno. Each piece of data is a piece of the puzzle that reveals new information about the volcanic nature of Io. Analyzing this is like a window into the past, present, and future of our solar system. At the end of last year, the NASA Juno probe captured the highest resolution images of this moon to date. Among these images, one taken on December 30th stands out, vividly showing Io's volcanic nature. This image, enhanced to highlight the details, shows a volcanic plume erupting from the surface of Io, with plumes reaching more than 60 miles, given that the diameter of the moon is about 2,200 kilometers. As Juno continues its journey around Jupiter, each orbit brings new opportunities, new challenges, and new discoveries. Among the planet's other 95 moons, Io stands out not only for its proximity to Jupiter, but also for the spectacular geological activity this proximity causes. The volcanic nature of the moon is a direct consequence of the enormous gravitational forces of Jupiter. Io is not a huge moon. It is only slightly bigger than the one orbiting our planet. However, as the largest planet in our solar system, Jupiter has tremendous gravity. This enormous force stretches and compresses Io, creating what is known as tidal heating. The orbit of the satellite is not a perfect circle, but is more like an ellipse, so the moon experiences different degrees of gravitational attraction from Jupiter as it approaches the planet. Its gravity stretches Io and compresses it as it moves away. This constant stretching creates tremendous internal heat, giving rise to its intense volcanic activity. This JunoCam image captures a plume of material ejected from the invisible volcano Prometheus, indicated by the red arrow. The plume is barely visible in the darkness below the terminator, the line dividing day and night. The image was taken by the spacecraft on October 15, 2023. Tidal heating is so intense that it turns Io's interior into a bubbling cauldron of molten rock. This heat gives rise to the volcanic activity that characterizes Io's landscape. Its surface is dotted with hundreds of volcanoes, some launching lava fountains up to hundreds of kilometers high. There are about 400 active volcanoes on Io, with about 150 erupting at any time. But Jupiter is not the only protagonist in this gravitational confrontation. The other Galilean moons, Europa, Ganymede, and Callisto, also exert their influence on Io. Their gravitational attraction helps maintain the orbit, so they play a crucial role in the tidal heating process. This complex gravitational interaction is a perfect example of how celestial mechanics determines a moon's fate. The tidal forces of Jupiter and its moons not only heat Io, but create a world where geological activity is the norm, not the exception. Io, a moon wrapped in fire and sulfur, plays a key role in Jupiter's great theater. Its incessant volcanic activity not only shapes the landscape, but also significantly affects the very nature of Jupiter's magnetosphere. As we mentioned earlier, this satellite's volcanoes are the most active in the solar system. In doing so, they expel enormous amounts of sulfur dioxide, or SO2, into space. This degassing, a direct result of intense internal heating, contributes to an atmosphere rich in sulfur compounds. But the influence of Io extends far beyond its own atmosphere. Since Io rotates within the enormous magnetosphere of Jupiter, and sulfur dioxide and other volcanic gases are ionized and become charged particles. These particles are trapped in Jupiter's magnetic field and form a plasma torus along Io's orbit. This torus, a bright ring of ionized particles, is a direct manifestation of the moon's volcanic power. The plasma torus is not a static feature, but changes in response to Io's volcanic activity. The expulsion of material from the volcanoes feeds the torus, affecting its density and composition. This complex interaction between Io's volcanism and the plasma torus illustrates the interconnectedness of the Jupiter system. It is also believed to be responsible for the powerful permanent auroras at the planet's poles. Volcanic emissions, once in the atmosphere, escape into space, where they undergo rapid renaturalization, a process that expels these particles at high speed in a plane perpendicular to the local magnetic field. This phenomenon can continue until the formation of extended sodium nebulae, adding another layer to the complex environment surrounding Jupiter. Observational studies have been crucial in shedding light on these interactions for many years. Telescopes like the TRAPPIST have followed the variability of Io's sodium cloud. These observations have shown that the physical properties of Io's sodium jets are highly variable and, interestingly, do not always correlate directly with the global brightness of Jupiter's plasma or the extended sodium nebula. This study highlights the complexity of the coupling between the surface atmosphere and the magnetosphere in the Jupiter system. Current research aims to reveal the precise mechanisms by which Io's volcanoes supply material to the plasma torus and how Io's sodium jet contributes to filling the magnetosphere's plasma reservoirs. Therefore, Io's incessant volcanic activity and its interaction with Jupiter's magnetic fields are not isolated phenomena, but play a fundamental role in shaping the dynamics of Jupiter's magnetosphere, producing plasma structures and neutron clouds that are key to understanding the complexities of planetary magnetospheres. Ongoing research and observations allow us to separate the layers of these interactions, offering a deeper understanding of the workings of our solar system. As we look to the future of space exploration, the fiery moon Io appears as a beacon of mystery and potential. The next phase of Io exploration is about to reveal secrets that have remained hidden beneath its stormy surface for centuries. We present the Jupiter Icy Moon Explore mission, abbreviated as JUICE, which aims to study the icy moons of Jupiter and offers interesting opportunities to advance our understanding of Io. Although the main objective of JUICE is Ganymede, Europa, and Callisto, its broad instrument set can provide valuable information about Io's dynamic environment. The dynamic environment of Io. The interplanetary spacecraft launched on April 14, 2023, from the Guiana Space Center in French Guiana by the European Space Agency. The ship is expected to arrive at Jupiter in July 2031, after 4 gravitational assists and an 8-year journey. As JUICE traverses the Jupiter system, its trajectory may offer opportunities to observe Io. These encounters could provide additional data on the volcanic activity of this satellite and its effect on the magnetosphere of Jupiter, complementing the conclusions extracted by missions directed directly to Io. Equipped with sophisticated instruments designed to study magnetic fields, the plasma environment, and atmospheric composition, JUICE can indirectly expand our knowledge of Io by studying Jupiter's magnetosphere. The Io Volcano Observer (IVO) mission is a bold initiative that represents the next leap in our search to understand this volcanic moon. IVO was a mission designed to study Io's intense volcanic activity, its subsurface structures, and the complex processes that drive its geological dynamism. The IVO mission is to enter orbit around Io and perform multiple close flybys equipped with state-of-the-art instruments. IVO will map Io's surface and take high-resolution images of its surface, as well as the areas of its intense volcanic activity, its underground structures, and the complex processes that drive its geological dynamism. The mission of IVO is to enter into orbit around Io and perform multiple close flybys equipped with state-of-the-art instruments. IVO will map the volcanic heat flows of Io, study the composition of the lava, and probe the internal structure of the moon. This mission aims to answer fundamental questions about the mechanisms of volcanism on Io and tidal heating's role in its activity. One of the most interesting aspects of the IVO mission is the exploration of the entrails of the moon. What is hidden under its burning facade? IVO seeks to shed light on this mystery by studying Io's internal structure. Seismic measurements and the analysis of the magnetic field can reveal the presence of underground magmatic chambers and provide information about the system of volcanic flows of the moon. The potential for new discoveries about volcanic mechanisms is enormous. IVO's observations could revolutionize our understanding of volcanic processes not only on Io, but throughout the solar system. By studying the unique volcanism of Io, we will be able to better understand the thermal evolution of planetary bodies and the role of tidal forces in the formation of planetary geology. Meanwhile, Juno continues its work with many more planned observations, not only of Io, but also of the other Galilean moons and, of course, Jupiter itself. The spacecraft will continue to operate until September 2025 or until it breaks down, whichever comes first. Meanwhile, we will wait with interest for more images taken during the next flyby. Imagine a canvas of moments woven with threads of time and matter that extends infinitely in all directions, capturing every choice, event, and heartbeat. What if we could navigate this intricate fabric? What if we could go back in time, look to the future, or even change the course of history? Time governs our lives, but it remains one of the most mysterious phenomena in the universe. We measure it, we chase it, but can we control it? The concept of time travel has intrigued humanity for generations, inspiring countless works of fiction and provoking rigorous debate. But what does science say? Could time travel ever pass from the pages of science fiction to the annals of scientific fact? Einstein's theory of relativity opened the door to this possibility by suggesting that time is not a constant, but a variable that can be manipulated. In addition, there are black holes, cosmic phenomena so powerful that they can distort not only light, but time itself. Did you know that astronauts aboard the International Space Station age more slowly than humans on Earth, even if only by a fraction of a second? This is not science fiction. It is a proven consequence of traveling at high speeds. So let's travel through the corridors of time. We will explore the scientific paradoxes and the unlimited possibilities that one day could make time travel a reality. Welcome to a journey through time. Long before the advent of science as we know it, Humanity was fascinated by the skies and the passage of time. Ancient civilizations paid attention to the stars, the sun, and the moon, and created elaborate calendars and methods for measuring time. Transported to the modern era, this fascination finds a new canvas in cinema and literature. The concept of time travel has been a recurring theme that offers both escapism and a platform for intellectual curiosity. In 1895, H.G. Wells wrote the novel The Time Machine, which not only popularized the term time machine, but also introduced the idea that time could be navigated as though through the dimensions of space. Then came Back to the Future, a pop culture phenomenon that took the concept of time travel and made it accessible to a new generation. Who could forget the DeLorean, the magnetic condenser, the flux capacitor, and the charming eccentricity of Doc Brown? His charming eccentricity? But it is not only a Western phenomenon. The charm of time travel knows no cultural or linguistic borders, from the Stein Gate in Japan to the profession of Ivan Vasilovich Chong in the Soviet Union. The theme of time travel resonates throughout the world. So, what attracts storytellers to this concept? The charm of rewriting history, the emotion of the unknown, or perhaps the philosophical questions that these journeys raise. It is a desire fueled by a mixture of nostalgia and expectation, a longing to relive fond memories or to launch into the promises of tomorrow. And now that we find ourselves on the cusp of scientific discoveries that could turn dreams into reality, the question becomes more important than ever. Could we, should we, and what would happen if we traveled through time? The blackboard is the canvas on which the abstract becomes possible. Here, equations like E equals mc squared are not just symbols, keys to understanding the universe, but could they unlock the secrets of time travel? From the big screen to living room televisions, time travel has been portrayed in countless ways. But let's put fiction aside and delve into the science that could make time travel more than just a plot device. Let's meet space-time, the four-dimensional fabric of our universe, according to Einstein's theory of relativity. Theory of relativity. This fabric can be bent and deformed by mass and energy, but can it be torn or twisted to create a path through time? Time dilation, a consequence of Einstein's theory, suggests that time flows at different speeds depending on the speed of movement or the gravitational field. For example, astronauts on the International Space Station age slightly slower than people on Earth. Experiments with particles, speed pedals, and atomic clocks have provided empirical evidence of time dilation. Particles traveling at speeds close to that of light have been observed to decay more slowly than their stationary counterparts. In addition, there are wormholes, hypothetical tunnels in space-time that, in theory, could shorten time and space. Although this is speculative, mathematics suggests that they are possible. Leading physicists and cosmologists have expressed their opinions on the matter, offering theories ranging from the plausible to the totally bizarre. Some even suggest that quantum mechanics, the science of the very small, could play a role in the possibility of time travel. And let's not forget the black holes, the mysterious titans of space. Their enormous gravity is so strong that it distorts not only space, but time itself. Could these cosmic phenomena be a gateway to other times? The scientific community is far from reaching a consensus. Time travel raises questions that challenge the very foundations of physics, from the nature of reality to the concept of causality. They say that time always moves forward and never backward. But what if we could take a leap forward, skipping years, decades, or even centuries? The idea might not be as far-fetched as it seems. When it comes to slowing down time, speed becomes the key parameter. According to Einstein's theory of relativity, the faster you move in space, the slower you move in time. So, could extreme speed be our ticket to the future? Believe it or not, time travel to the future has already occurred, albeit on a minuscule scale. Astronauts aboard the International Space Station experience time dilation and age slightly slower than their counterparts on Earth. Let's now focus on the twin paradox, the famous thought experiment that takes time dilation to another level. Let's imagine two twins separated at birth. One travels through space at a speed close to that of light, while the other remains on Earth. Upon reuniting, the space twin will appear younger. Reaching speeds close to that of light would greatly enhance this effect. But such speeds are currently beyond our technological reach, not to mention that the energy requirements would be astronomical. Scientists and engineers are grappling with these problems and investigating propulsion technologies that could one day make it possible to travel at speeds close to light. But even then, could the human body withstand such a journey? Let's imagine a future in which time dilation capsules are as common as airplanes, allowing people to jump into the future to glimpse advanced civilizations or even avoid catastrophes. Will knowledge of the future be a gift or a curse? And what will it mean for the concept of freedom? Music from science fiction to scientific articles. Wormholes have captured our collective imagination. These hypothetical tunnels in the fabric of space-time could become the cosmic shortcuts we've been dreaming of. But what are wormholes, and could they be the key to time travel? Imagine folding a piece of paper so that 2 points touch, and then poking through it with a pencil in space-time. The wormhole would be that pencil, creating a straight path between 2 distant points. This concept gained popularity in the scientific community thanks, in part, to Carl Sagan. While writing his novel Contact, he consulted physicist Kip Thorne to explore the scientific possibility of using a wormhole to travel between stars. Today, physicists are delving into the mathematics of wormholes. While the general theory of relativity allows for their existence, the equations also assume that they collapse too quickly for anything to pass through. In theory, by introducing some exotic matter, for example, one could counteract the gravitational forces that cause the wormhole to collapse, keeping it open long enough for something or someone to pass through. The representation of wormholes in popular media often overlooks these complexities. They are usually depicted as stable luminous vortices, but the reality, if they exist, may be much more volatile and unpredictable. Despite the lack of empirical data, wormhole study is a dynamic research area. Scientists use computer models and indirect observations to understand their properties and possible uses. Let's imagine the possibilities if wormholes could be used for time travel. One end could be anchored in the present and the other in the future or past. The implications for research and even for preventing global catastrophes are astonishing. Wormholes open the door to questions not only about where we could go, but also when. As we approach the possible discovery of these cosmic shortcuts, we must ask ourselves if we are prepared for the responsibility that such power entails in the world of the very small, where particles are also waves and reality itself seems diffuse. In the quantum world, this region of uncertainty could hold the keys to unlocking time travel. Quantum mechanics challenges our everyday understanding of the world. Let's take the double-slit experiment, in which particles behave like both particles and waves. This duality suggests that, at the quantum level, the fabric of reality is much more malleable than we thought. Great minds like Richard Feynman and Niels Bohr have delved into the mysterious world of quantum mechanics, a theory that has been incredibly successful in explaining the behavior of matter and energy at extremely small scales. Some physicists suggest quantum mechanics could offer a basis for time travel. Quantum tunneling, for example, allows particles to pass through barriers like ghosts through walls. In the example of the double slit, could a similar principle allow time tunneling? Quantum computing is a new field that uses the principles of quantum mechanics to perform calculations at speeds unimaginable for classical computers. Some speculate that quantum algorithms could solve equations related to time travel that are currently too complex for current computers. The concept of quantum entanglement adds interest. Imagine 2 particles joined in a certain way. Once entangled, these particles become interconnected, forming a single quantum system. The truly amazing aspect of entanglement is that the state of one particle instantaneously affects its entangled partner, regardless of the distance that separates them, whether on the other side of the room or even on the other side of the galaxy. If the spin of one changes, that of the other changes instantaneously. Albert Einstein called it spooky action at a distance. At first, he did not like this idea because it seemed to violate the speed of light limit established by his theory of relativity. However, since then, numerous experiments have confirmed that entanglement is a real and fundamental aspect of quantum mechanics. He didn't like this idea because it seemed to violate the speed of light limit established by his theory of relativity. However, since then, numerous experiments have confirmed that entanglement is a real and fundamental aspect of quantum mechanics. Could a remote effect like this make a difference in instantaneous time travel? Although the intersection between quantum mechanics and time travel remains the subject of speculation, it is a hot topic in scientific research. Researchers are studying everything from quantum time loops to the role of quantum gravity in the early universe. Let's imagine a future in which the principles of quantum superposition could explain multiple timelines or realities. What if we could exist in a superposition of the past and present? Could quantum mechanics be the final piece of the puzzle in our quest to conquer time? Let's move on from the world of the microscopic scale to the grandly large. Black holes, mysterious titans of space whose gravity is so strong that not even light can escape them. But could these celestial phenomena hold the secret to time travel? Enter the concept of closed time-like curves. A closed time-like curve, or CTC, is a path in space-time that repeats on itself. In theory, an object, or even a person traveling along a CTC, could end up at an earlier point in time. The idea was first proposed by physicist Kurt Gödel in 1949. Gödel's solution suggested that rotating universes could contain looping paths in time. However, these solutions required certain conditions, such as a universe full of rotating matter. Although Gödel's model is considered physically implausible in most cases, it has opened the door for other scientists to explore the concept. The main challenge is to find a scenario in which CTCs can exist without violating the laws of physics. One such scenario involves rotating black holes known as Kerr black holes. The enormous gravitational and rotational forces can, in theory, twist spacetime into loops, creating CTCs, but there is a problem. Most models predict that the center of a rotating black hole, known as a singularity, will be ring-shaped instead of point-shaped. This ring feature could potentially serve as a gateway to CTCs, but the powerful gravitational forces could also create a barrier known as the Cauchy horizon, beyond which the laws of physics are violated. The study of CTCs and black holes is fraught with paradoxes and uncertainties. For example, if CTCs exist, they can lead to paradoxes in which cause and effect are reversed. This has led some physicists to propose the chronology protection hypothesis, which suggests that the laws of physics prevent such paradoxes. Imagine the possibilities and dangers of approaching a rotating black hole. Could we ever safely navigate such a perilous region of space-time? And if we could, what might we find on the other side? Another universe or another time? In addition to black holes and closed time curves, another cosmic mystery could open a path through time: cosmic strings. These hypothetical one-dimensional cracks could be remnants of the Big Bang itself. Cosmic strings are believed to have formed in the early universe, cooling after the hot, dense state of the Big Bang. These strings would have been thinner than an atom, but incredibly dense and had tremendous gravitational force. Although still theoretical, cosmic strings offer interesting possibilities for time travel. Physicists J. Richard Gott and William Hiskok have made important contributions to our understanding of these objects. Gott suggested that a cosmic string traveling at the speed of light could, in theory, distort space-time enough to create a loop that would allow travel to the past or the future. However, the existence of cosmic strings remains a point of debate. Their detection would require astronomical observations on scales currently beyond our capabilities. Furthermore, if they existed, harnessing their power for time travel would be quite a challenge. Let's return now to quantum entanglement. We have already explored how entangled particles are connected in ways that transcend spatial distances. Can they be linked in time? Some theories suggest that entangled particles can transmit information not only in space, but also through time. Let's imagine a future in which quantum entanglement is used to create a kind of quantum internet that allows instantaneous communication between eras. The intersection of cosmic strings and quantum entanglement is a frontier of theoretical physics, full of unanswered questions and untapped potential. Researchers are exploring how both phenomena could connect and what this could mean for our understanding of time travel. Imagine a scenario where cosmic strings are manipulated at the quantum level through entanglement. This would represent a fusion of the very large and small, a meeting point between the cosmic and quantum scales that could revolutionize our concept of time travel. As we delve into the realm of time travel, we face many paradoxes and enigmas. These are not just intellectual exercises, but fundamental questions that could make or break the possibility of time travel. First, there is the grandfather paradox. Imagine you go back in time and prevent your grandparents from meeting. If they never meet, one of your parents will never be born and, therefore, neither will you. But if you were never born, how could you have traveled in time? The grandfather paradox raises questions about causality and the very nature of time itself. Some theorists suggest that these paradoxes can be resolved by the existence of parallel universes, where each resolution generates a new timeline. Another confusing paradox is the so-called bootstrap paradox, named after the popular expression, pulling oneself up by the bootstraps. Imagine you go back in time to give Shakespeare a copy of your plays, which he then claims as his. In that case, where did those works originate? The bootstrap paradox creates a closed loop of cause and effect with no apparent origin. It challenges our linear understanding of time and suggests that cause and effect may not be as simple as we think. Another paradox is the predestination one. Occurs when a time traveler's actions in the past lead to the event he was trying to avoid. This raises questions about free will and determinism, and about whether we can really change the course of history. The study of time travel paradoxes is not just a game for philosophers, but a serious area of research in physics and metaphysics. Resolving these paradoxes could shed more light on time travel. As we stand on the threshold of scientific discovery, the future of time travel remains a mystery shrouded in paradoxes, theories, and cosmic phenomena. What was once the realm of science fiction is gradually approaching the realm of real science. From cosmic strings to quantum entanglement, from rotating black holes to closed time curves. We explore the theories and possibilities that could one day make time travel a true reality. Current research is paving the way for new experiments, new technologies, and perhaps even a new understanding of the structure of reality. But as we teeter on the edge of cosmic horizons, one question becomes more important than all others. Are we prepared for what we might find? Time waits for no one, but what if we could wait on time? What if the closest star to the Sun, Proxima Centauri, hides a world where humans could someday live? In 2016, astronomers discovered Proxima Centauri b, a planet just 4 light years away. But reaching this distant neighbor is not just a dream. It is a challenge that modern science has begun to address. Imagine a journey of more than 25 trillion miles. The technology we have today, such as the ionic engines used in deep space missions, pales compared to what would be needed for such a trip. But hidden in plans from a decade ago and in cutting-edge research are keys to interstellar travel. But distance isn't the only obstacle we have to overcome today. We will discuss it and discover if humanity's next great leap can take us to Alpha Centauri. The dream of interstellar travel has been part of the human imagination for centuries, but it was not until the 20th century that science began to catch up with science fiction. The journey begins with a momentous event in 1961, when Yuri Gagarin became the first man to orbit Earth. This achievement paved the way for space exploration, showing that human beings could survive and work beyond our planet. Then came the Apollo program, which included the historic 1969 moon landing. The steps of Neil Armstrong and Buzz Aldrin on the lunar surface were not only a victory for humanity, but also a demonstration of our ability to reach other celestial bodies. In the 1970s, the Voyager missions provided invaluable data about the outer planets and heliosphere. These probes, which are now in interstellar space, carry with them gold records with messages intended for any intelligent extraterrestrial life form that may find them. The voyages of Voyager 1 and 2 have allowed us to glimpse the immensity of space and the inspiring potential of travel beyond our solar system. But humanity does not stop there. In recent years, the development of advanced propulsion systems has been crucial. The ionic engines used in missions such as NASA's Dawn spacecraft allow for long missions with unprecedented efficiency. These engines use electrically charged particles to generate thrust, a more efficient method than traditional chemical rockets. At the same time, our understanding of the universe has been revolutionized by the discovery of exoplanets, planets orbiting stars outside our solar system. The first confirmed exoplanet was discovered in 1992, when astronomers discovered two rocky planets orbiting a pulsar. This discovery broke previous notions and opened the door to the search for other worlds. In 1995, the discovery of 51 Pegasi b, the first exoplanet found orbiting a star like the Sun, further reinforced the idea that planets are common in the universe. This gas giant, about 50 light-years away, marked the beginning of an era of exoplanet discoveries that continues to this day. Among the most exciting discoveries is Proxima Centauri b, discovered in 2016. This exoplanet orbits Proxima Centauri, the star closest to our Sun, at only 4 light-years. 24 light-years. Proxima Centauri b is located in the habitable zone of its star, where all the conditions for the existence of liquid water could occur. This proximity and its potential habitability make this planet a priority target for future exploration and even possible colonization. The discovery of Proxima Centauri b was made possible by the radial velocity method, which makes it possible to detect subtle fluctuations in the movement of the star caused by the gravitational attraction of the planet orbiting around it. So far, this method has helped to identify more than exoplanets, each of which has become the next step in the search for a world in which life can exist. The feasibility of interstellar travel depends directly on our ability to develop powerful and efficient propulsion systems. Current space travel technology has made significant advances, but it is still far from what is needed to travel beyond our solar system. Ionic engines represent one of the most advanced forms of space propulsion in use today. Unlike traditional chemical rockets, which use explosive reactions to create thrust, ionic engines use electricity to ionize propellant, usually xenon gas. The ionized gas is then accelerated using an electric field, creating a sustained and very efficient thrust. NASA's Dawn spacecraft, launched in 2007, is an excellent example of the capabilities of ionic propulsion. Dawn's mission was to explore the asteroid belt, in particular the protoplanet Vesta and the dwarf planet Ceres. Ionic propulsion allowed Dawn to enter and exit orbits around these bodies, which would have been too expensive with conventional rockets. Ionic engines have a high specific impulse, meaning they use fuel more efficiently than chemical rockets. This efficiency is critical for long missions, as it allows spacecraft to carry less fuel. However, the disadvantage is that ionic engines produce much less thrust than chemical rockets. This makes them unsuitable for launching spacecraft from Earth's surface, where enormous thrust is needed to overcome gravity. Another milestone in the development of modern propulsion technologies was the New Horizons probe, launched in 2006. The spacecraft was to explore Pluto and its moons, providing humanity with the first images of this distant world from a very close distance. The probe journey did not stop at Pluto, but continued toward the Kuiper Belt, a region full of icy bodies and remnants from the solar system's formation. New Horizons used a combination of chemical propulsion and gravitational assist to reach its high speed. After launch, the spacecraft received gravitational assist from Jupiter, which increased its speed and directed it toward Pluto. This maneuver allowed New Horizons to travel more than 3 billion miles in just 9 years, an amazing achievement given the enormous distances. While New Horizons demonstrates the current level of space travel capabilities, it also highlights its limitations. Despite reaching speeds of over 36,000 miles per hour, it took the spacecraft nearly a decade to reach Pluto and longer to continue to the Kuiper Belt. For interstellar travel, where distances are measured in light years, we need propulsion systems capable of reaching much higher speeds for long periods. Meanwhile, the most intriguing and historically significant concept of advanced propulsion is nuclear pulse propulsion. This technology, conceived during the Cold War, involves using controlled nuclear explosions to propel a spacecraft. The concept was first proposed by physicist Stanislaw Ulam in the 1950s and subsequently developed in Project Orion. The basic principle of nuclear pulse propulsion is simple. Small nuclear bombs are launched behind the spacecraft, detonated, and the resulting explosions provide thrust. A large pusher plate, attached to the spacecraft, absorbs the force of the explosion and propels the ship forward. The potential of the Proyecto Orion was enormous. Calculations showed that a spacecraft of this type could reach speeds of up to 10% of the speed of light, which would make it one of the fastest of the proposed propulsion methods. Such capacity would reduce travel time to nearby star systems, including our neighbor Alpha Centauri. Meanwhile, the Breakthrough Starshot initiative has become one of the most ambitious attempts to achieve interstellar travel in recent years. The goal of this international scientific project is to send a probe to Alpha Centauri and possibly reach it in just 20 years. The main innovation of Breakthrough Starshot is the use of a light sail propelled by a series of powerful terrestrial lasers. This light sail, a thin and highly reflective sheet, will accelerate to extremely high speeds by transmitting the impulse of millions of laser beams. Unlike traditional propulsion methods, this system does not carry fuel, which makes it extremely light and, in theory, capable of reaching speeds of up to 20% of the speed of light. However, the realization of this technology presents challenges. The proposed laser array would require a total optical power of about 100 gigawatts, about 100 times the capacity of the synchronizing approximately 100 million lasers to focus their beams on the light sail is a technical obstacle of great magnitude. To solve this, researchers at the National University of Australia have proposed using a laser guide satellite to help maintain a precise target throughout the journey. Despite these challenges, the potential benefits of this technology are significant. If successful, the Breakthrough Starshot mission will be able to transmit detailed scientific data and images of Alpha Centauri, which will provide an unprecedented view of our closest star. Music system. While solar sails represent a promising technology for the near future, other cutting-edge concepts are expanding our understanding of physics. Among them is the theoretical warp engine, inspired by Einstein's general theory of relativity. A warp engine would manipulate space-time itself, compressing space in front of the spacecraft and expanding it behind, allowing the ship to travel faster than the speed of light without violating the laws of physics. The concept of warp propulsion gained attention after the 1994 publication of an article by physicist Miguel Alcubierre, who proposed a theoretical basis for such an engine. Although the concept is speculative and requires exotic matter with negative energy density, warp propulsion remains a tempting possibility. For future interstellar travel, another innovative concept is the interstellar engine of Freeman Dyson. This hypothetical propulsion system would harness the energy of a star using mirrors or lenses to concentrate stellar energy on a spacecraft. The collected energy would then be converted into thrust, propelling the ship to high speeds. Although the Dyson concept is intriguing, its practical realization faces significant obstacles. Capturing and converting enough stellar energy to achieve significant thrust would require materials and engineering capabilities far greater than our current technology. Perhaps the most powerful of the proposed propulsion systems is one based on antimatter. When antimatter comes into contact with matter, both particles are annihilated, releasing enormous amounts of energy. A spacecraft propelled by antimatter could, theoretically, reach speeds close to a significant fraction of light speed. The potential of antimatter propulsion is amazing, and so are the challenges it poses. The production of antimatter is currently very inefficient and costly, and its safe storage poses challenges due to its highly reactive nature. Despite these obstacles, research on antimatter continues, as it promises to be an engine of unprecedented efficiency. The enormous distances represent the most obvious obstacle. However, even with a modestly efficient propulsion system, only a fraction of the difficulties would be overcome. Interstellar travel is a huge undertaking, fraught with technical and logistical challenges. Even with the most advanced propulsion systems, traveling to our nearest star system, Alpha Centauri, requires overcoming significant technical obstacles. One of the main technical problems is protection from radiation. Space is full of high-energy particles from the sun and distant sources. Prolonged exposure to this radiation can be deadly to humans and sensitive electronic equipment. Modern spacecraft use a combination of physical and electronic shielding to protect themselves from radiation, but these methods are insufficient for the prolonged exposure expected during interstellar travel. Advanced materials and innovative shielding techniques are being investigated, including the use of magnetic fields to deflect charged particles and the development of new composite materials that provide better protection without excessive weight gain. However, creating effective and lightweight radiation shielding remains a major challenge. Another technical obstacle is maintaining the structural integrity of the spacecraft in the long term. Ships designed for interstellar travel must be able to withstand the stresses associated with launch, long stays in space, and potential collisions with micrometeorites and other space debris. The high speeds required for interstellar travel exacerbate these risks, since even the smallest particles can cause significant damage at such speeds. Engineers are exploring advanced materials, such as carbon composites and reinforced alloys, to improve spacecraft durability. In addition, modular designs that allow in-flight repair and maintenance could be critical for long-duration missions. The immensity of space presents another logistical challenge. Even at a significant fraction of light speed, it would take decades to reach the nearest star systems. Advances in autonomous systems and long-term life support are needed to keep a spacecraft running reliably for so long. Solutions, such as hibernation or suspended animation, are being explored, but these technologies are still in the experimental phase. In addition to technical and logistical challenges, interstellar travel faces serious economic and political obstacles. The cost of developing, building, and launching an interstellar mission is astronomical, no pun intended. Governments, private companies, and international consortiums will have to collaborate and contribute resources. Historically, space exploration has been financed mainly by national governments, but the increasing participation of private companies like SpaceX and Blue Origin suggests a shift toward more diverse financing models. The search for habitable planets, especially in the Alpha Centauri system, is one of the key areas of modern astronomy. As you may have realized, the discovery of Proxima and Tor in 2016 was an important milestone that demonstrated the possibility of habitable worlds existing in the star system closest to us. This exoplanet has given rise to numerous research missions and initiatives aimed at determining its characteristics and potential to harbor life. To continue this research, the European Southern Observatory has developed a new instrument specifically designed to search for exoplanets in the Alpha Centauri system. This advanced instrument, part of the Very Large Telescope in Chile, improves our ability to detect Earth-like planets by improving the precision of radial velocity measurements. The instrument aims to identify Earth-sized planets by detecting the tiny gravitational fluctuations they cause in their host stars. Focusing on Alpha Centauri A and B, the two Sun-like stars in the system, this instrument seeks to detect additional planets that may be found within their habitable zones. The improved sensitivity and resolution of this technology promise to reveal planets not previously detected, giving us a clearer picture of the potential for habitable worlds in our nearest star system. The importance of discovering a habitable planet in the Alpha Centauri system cannot be underestimated. Such a discovery would be a huge step forward in our quest to understand how far habitable conditions extend beyond our solar system. Such a nearby habitable planet would be an ideal candidate for future interstellar missions and a possible target for human colonization. Recent discoveries in the search for habitable exoplanets have been promising. For example, late this spring, astronomers discovered the Earth-like exoplanet LISA 12b, located just 40 light-years away. This planet, comparable in size to Venus, orbits a red dwarf star, and scientists estimate it has a surface temperature of about 107 degrees Fahrenheit. The discovery of such a nearby planet is a major step forward in the search for extraterrestrial life. LISA 12b is located just 40 light-years away. This planet, comparable in size to Venus, orbits a red dwarf star, and scientists estimate it has a surface temperature of about 42 degrees Celsius. The discovery of such a planet, which could have an atmosphere, provides information about the conditions necessary for a planet to retain an atmosphere and for liquid water to exist. The discovery was made possible by NASA's satellite for the study of exoplanets in transit, which detects exoplanets by observing a small, fainter star as the planet passes in front of it. During these transits, the light from the star passes through the atmosphere of the exoplanet planet's atmosphere, allowing astronomers to analyze its composition using transmission spectroscopy. The importance of LISA 12b goes beyond its potential habitability, as it serves as a valuable point of comparison for understanding why Earth and Venus, despite their similarities, have very different environments. By studying LISA 12b, scientists hope to learn more about atmospheric retention and the evolutionary pathways of Earth-like planets orbiting cool stars, which are the most common type of stars in the Milky Way. It is estimated that the size of LISA 12b may be as large as Earth or slightly smaller, comparable to Venus in our solar system. Current efforts to find and study potentially habitable planets around Alpha Centauri and other nearby stars continue to evolve. Instruments such as the JWST are expected to play a crucial role in this search, providing a deeper understanding of the conditions that could make these planets habitable. On the other hand, no one says that humans should be the first to explore these distant worlds. Even without the advanced technology needed for human survival, we can send probes to pave the way. Intelligent robotic probes and artificial intelligence have a key role to play in the future exploration of interstellar space. These technologies can operate autonomously, performing complex tasks without direct human intervention, making them ideal for long-duration missions far beyond our solar system. One of the most intriguing concepts in this regard is that of the so-called von Neumann probes. These theoretical self-replicating machines could explore the galaxy using local materials to create their replicas, exponentially increasing the number of probes with each replication. This approach could provide thorough exploration and possible colonization without the need for constant resupply from Earth. However, when it comes to human space exploration, the idea of interstellar arcs and self-sufficient habitats represents a visionary approach to colonizing distant star systems. These enormous spaceships would house large communities and provide everything necessary to sustain life during multi-generational journeys to other stars. These habitats would be equipped with advanced life support systems, agricultural facilities, and social infrastructure to ensure the well-being of their inhabitants. In conclusion, although our current technology limits us to relatively modest space travel, these advanced concepts offer a glimpse into a future in which we can transcend the spatial barriers that confine us to our solar system. As technology advances, these concepts could move from science fiction to reality, paving humanity's way to the stars. Music. The moon has always been a beacon of mystery and wonder. But beyond its radiant beauty and folklore tales, the moon hides secrets that have eluded us for centuries. Among these mysterious features is the lunar South Pole, a region shrouded in perpetual shadow and intense cold, untouched and unexplored by any previous lunar mission. This is the story of Chandrayaan-3. India Chandrayaan-3 embarked on a journey of more than 238,000 miles. Its purpose was to unravel the mysteries of the moon's South Pole, a place where sunlight barely reaches and the terrain is so treacherous that you have to make your way through an endless maze of craters and rocks. A place where sunlight barely reaches, an area where the terrain is so treacherous that you have to make your way through an endless maze of craters and rocks. Here, in this alien landscape, Chandrayaan-3 sought answers to questions that have intrigued scientists for decades. What lies beneath the surface of this mysterious region? Do earthquake-like tremors shake this silent world? And the most exciting question is whether water, the elixir of life, exists here in the form of ice. As Chandrayaan-3 ventured beyond Earth, it carried with it the aspirations of a nation and the curiosity of the world. Its main objective was clear, but difficult to achieve: a soft landing near the moon, a feat never before achieved. From the busy control center of the Space Research Organization of India, a team of dedicated scientists and engineers piloted this ambitious mission. Their experience helped Chandrayaan-3 cross the vacuum of space, overcoming the challenges of insertion into lunar orbit and descent. The south pole of the moon is a landscape unlike any other. Here, the terrain is a mosaic of craters and mountains, many shrouded in perpetual darkness. The challenge was not only to land, but to do so safely in an area where the terrain is relentless and most slopes are quite steep. When the Vikram landing module separated from the orbiter, the descent began. The landing module, equipped with advanced sensors and engines, began its perilous journey to the surface of the moon. Imagine a spacecraft autonomously navigating a maze of craters and rocks in search of terrain safe enough for landing. The systems on board the landing module worked tirelessly, analyzing every centimeter of the terrain below. Facing this treacherous landscape, the landing module also struggled against extreme temperatures. The south pole of the moon is a place of extreme contrasts. The sun barely rises above the horizon, while the shadows hide frigid temperatures that can drop to minus 382 degrees Fahrenheit. As the landing module made its final approach, the hearts in the flight control center beat fast. Every second was decisive, every maneuver a test of human ingenuity and technological prowess. With a slight bump, the Vikram landed, marking a historic moment not only for India, but for lunar exploration in general. In the silence of the lunar South Pole, Chandrayaan-3 began its mission of exploration and discovery. Thus, after the historic landing of Chandrayaan-3, a new chapter in lunar exploration began. The objective of the mission was to maximize the study of the characteristics of the moon, especially its elusive exosphere and ionosphere, and to establish the range of temperature variations just below its surface. The lunar exosphere, the thin layer of gases that surrounds the moon, holds the key to the satellite's past and present. Unlike the robust terrestrial atmosphere, it is so rarefied that it almost resembles a vacuum. The instruments of Chandrayaan-3, developed with the latest technology, are designed to measure the density and composition of this elusive layer. In addition to the exosphere, the mission delves into the lunar ionosphere. This layer, formed by solar energy that ionizes the atoms of the exosphere, plays a crucial role in lunar communications and navigation. The measurements from Chandrayaan-3 were designed to provide unprecedented information on the density and behavior of the ionosphere, important for future lunar missions and potential human habitats. Another intriguing aspect of the mission was the study of temperature variations just below the lunar surface using one of the landing module's 4 instruments, the CHASTE, or Chandra Surface Thermophysical Experiment. The temperature probe, submerged in the lunar regolith, had the critical mission of mapping the thermal profile of the lunar soil. The results from Chandrayaan-3 revealed a strong contrast in surface temperatures during a lunar day. Temperatures rose drastically to 60 degrees Celsius. While at only 8 centimeters deep, they dropped significantly to minus 10 degrees Celsius, demonstrating that the lunar soil is a potential thermal insulator. This discovery opened new opportunities for future lunar habitats, as it suggests that the lunar regolith could serve as a thermal insulator to protect astronauts from the harsh extreme temperatures and harmful radiation of the moon. These studies were more than just scientific efforts. They were steps toward a future in which the moon could be a gateway to space exploration. The results of the mission on the exosphere, The ionosphere and the temperature of the lunar subsoil laid the foundations for understanding the environment of the moon and its potential to harbor human life. In the vast lunar landscape, Chandrayaan-3 was ready to detect a phenomenon not observed in more than 50 years, a moonquake. The mission managed to shed light on one of the most intriguing and least understood aspects of the moon. The Instrument for Lunar Seismic Activity, or ILSA, a seismic instrument designed to detect the slightest tremors on the moon, achieved it. Chandrayaan-3 detected what appeared to be a moonquake, a significant discovery, given that the last such observation was made during the Apollo missions in the early 1970s. Moonquakes are fundamentally different from terrestrial earthquakes. The seismic activity of the Earth is largely due to the movement of tectonic plates. The moon, which lacks these plates, experiences earthquakes for various reasons. These tremors can last much longer than earthquakes, sometimes up to an hour, and their origin is a matter of scientific interest. The data from Chandrayaan-3 suggests several possible causes for these earthquakes. One theory is collision with meteorites, which could cause shock waves that penetrate the. Another is the gravitational force of the Earth, which causes tidal forces that load the lunar crust. Finally, extreme temperature fluctuations on the lunar surface can cause expansions and contractions that lead to earthquakes. These earthquakes are not only superficial phenomena, but windows into the interior of the moon. By analyzing seismic waves, scientists can deduce the composition and structure of our satellite's interior, which resembles an ultrasound of the lunar interior. This information is of great importance for understanding the formation and evolution of the moon. The detection of a moonquake by the Chandrayaan-3 spacecraft has not only allowed a glimpse into the dynamic nature of our celestial neighbor, but has also opened new perspectives on the geological processes that shape the moon to unravel its geological mysteries. The Chandrayaan-3 carried out another exploration. Among the most intriguing findings is the discovery of sulfur, an element whose presence on the moon has been shrouded in mystery. The Laser-Induced Decomposition Spectroscope, or LIBS rover, a marvel of scientific instrumentation, vaporizes small soil samples using high-energy laser pulses. When the plasma emits light, the spectroscope analyzes its wavelength, thus revealing the presence of various elements, including sulfur. Sulfur's presence on the moon is a significant finding. On Earth, sulfur is often associated with volcanic activity, raising questions about similar processes on the moon in the past. Its presence could provide information about the volcanic history of the moon and the processes that shaped its surface. In addition to sulfur, another key objective of Chandrayaan-3 was the search for water ice, a search that has intrigued scientists for decades. Water ice on the moon is not only a scientific curiosity, but also a potential resource for future human missions, as it provides water for life support and fuel production. Despite great hopes, Chandrayaan-3, like its predecessors, did not find direct evidence of water ice on the lunar surface of the moon. However, the lack of direct evidence is not a conclusion, but a clue that leads to new hypotheses. One theory is that of the cold trap, in which water vapor can migrate to permanently shadowed craters at the poles and freeze into ice. The detection of sulfur adds another layer to this theory, since sulfur can be trapped with water ice and released as a result of the decomposition of water molecules by high-energy solar radiation. The lack of direct evidence of water ice raises important questions. Is the ice located deeper under the surface, protected from detection by the insulating properties of the lunar soil, or is its prevalence more heterogeneous and difficult to detect than previously thought? During its exploration of the south pole of the moon, Chandrayaan-3 found more than just sulfur. The LIBS instrument of the rover performed the first in situ measurements of the elemental composition of the lunar surface in this region. In addition to sulfur, the instrument detected aluminum, calcium, iron, chromium, and titanium, each of which reflects part of the complex geological history of the lunar surface. Other measurements added new details to this discovery, further revealing the presence of manganese, silicon, and oxygen. Each of these elements, with its own unique spectral signature, provides clues about the moon's formation and its evolutionary history. Studies on the presence of hydrogen, a key component in the search for water, also continue. The mission's discovery of these elements and the ongoing search for water underscores the dynamic and complex nature of lunar geology. Each discovery, each unanswered question, brings us closer to understanding our closest celestial neighbor and prepares us for the next steps in lunar exploration. The Chandrayaan-3 mission to the south pole of the moon opened a new chapter in lunar exploration and also paved the way for the next ambitious leap, the LUPEX Lunar Polar Exploration Mission, for its acronym in English. This joint initiative between the Indian Space Research Organization and the Japan Aerospace Exploration Agency is scheduled to launch no earlier than 2026. LUPEX plans to send an unmanned lunar lander and rover to further explore the South Pole region of the moon. JAXA will likely provide the H-3 launch vehicle and the rover, currently under development, and ISRO will provide the lander. This mission represents a significant step in international cooperation in lunar exploration. Are multiple. It will demonstrate new surface exploration technologies, fundamental for sustained lunar exploration in the polar regions. Precise landings will be achieved through the use of a feature matching algorithm and navigation equipment derived from the JAXA Smart Lander for investigating Moon. The LUPEX rover will carry several instruments from JAXA and the ISRO, including a drill capable of collecting samples at a depth of 15 meters. 5M. The search and analysis of water are key objectives of the mission, and the possible discovery of water ice could be a major breakthrough for future lunar missions. Parallel to LUPEX, the ISRO Chandrayaan-4 mission, designed to bring samples from the moon, is in the planning phase and is scheduled to launch in 2028. Chandrayaan-4 will consist of 4 modules: a transition module, a descent module, an ascent module, and a reentry module. The ambitious goal of the planned mission is to bring soil samples from the moon, which will provide invaluable information about the lunar environment. The mission will involve complex maneuvers, including sample collection, docking in lunar orbit, and the return of samples to Earth. The innovative discoveries of Chandrayaan-3, from the detection of sulfur and other elements to the study of lunar earthquakes, have revealed new layers of the moon's mysterious nature. These results provide crucial information about the geology of the moon, its internal structure, and the potential for future lunar habitats. Looking ahead, the future of lunar exploration looks promising. Missions like LUPEX and Chandrayaan-4, building on the legacy of the previous ones, will continue to explore the mysteries of the moon. India's role in these efforts is not only that of a participant, but also as a pioneer. These events inspire us to look beyond, toward the infinite mysteries of the cosmos. The deeper we delve into the universe, the more mysteries it reveals to us. Gravity, the invisible force that holds the cosmos together, may not be as immutable as we once thought. From ancient civilizations to Einstein's revolutionary discoveries, our understanding of gravity has constantly evolved. However, recent discoveries suggest that there could be a large-scale cosmic failure, a subtle deviation in the force that governs galaxies and stars. Ancient scientists wondered about the nature of gravity, laying the foundations for Newton's elegant laws, but it was Einstein, in the early 20th century, who changed our perception. His theory of general relativity describes gravity not as a force, but as a curvature of space-time itself. Despite its success in predicting phenomena such as black holes and gravitational waves, Einstein's theory has its limitations when we turn our gaze to the scale of galactic clusters. Beyond, we find inconsistencies. Gravity seems to weaken slightly over billions of light years, and this phenomenon is what researchers now call a cosmic failure. This anomaly could point to new physics, perhaps an extension of the standard cosmological model to include a variable gravitational constant. Such a modification could reconcile these inconsistencies without overturning the established successes of general relativity. The discovery of a cosmic failure forces us to rethink our understanding of gravity. Could this be the first clue to a new puzzle that will eventually lead us to a theory that unifies the fundamental forces of nature? Long before the scientific revolution, ancient civilizations had already encountered the concept of gravity, although they understood it in very different ways. The Greeks, for example, believed in the geocentric model, in which the Earth was the center of the universe. Aristotle argued that objects fall toward their natural place, and this theory dominated Western thought for centuries. In ancient India, Hindu scriptures describe the concept of gravity as an inherent force that attracts objects to Earth. Similarly, the Chinese philosopher Mozi, in the 4th century A.C., suggested that objects fall due to the force of Earth's energy. These are early ideas, though primitive by modern standards, that laid the foundation for future scientific research. It was not until the Renaissance that a more accurate understanding arose. The work of Copernicus, Galileo, and Kepler challenged Aristotelian views, paving the way for the pioneering work of Isaac Newton. Newton's formulation of the law of universal gravitation in the 17th century was a monumental leap. He described gravity as the force that attracts two bodies to each other in proportion to their masses and inversely proportional to the square of the distance between them. This elegant equation unified the sky and earth under a single universal law. At the beginning of the 20th century, Albert Einstein revolutionized our understanding of gravity by proposing the general theory of relativity, according to which gravity is not a force, but a curvature of space-time caused by mass and energy. Einstein's equations suggested that massive objects, such as stars and planets, deform the fabric of space-time, creating what we perceive as gravity. This concept was visually confirmed during the solar eclipse of 1919 in an expedition led by Sir Arthur Eddington. By observing the curvature of starlight around the sun, Eddington provided one of the first experimental confirmations of the general theory of relativity. Consider that almost a century ago, Einstein added an adjustment factor to his equations to fit the then-accepted idea of a static universe, and later called this factor his biggest mistake. However, this lambda constant reappeared many years later to explain the accelerated expansion of the universe. Einstein's theory also predicted phenomena such as black holes and gravitational waves, which we have only recently begun to observe, further confirming the validity of his theory. The image of the event horizon of a black hole captured by the Event Horizon Telescope image of a black hole in 2019 and the detection of gravitational waves by LIGO in 2015 were monumental achievements in modern astrophysics. However, despite its successes, general relativity has its limitations, as it is inconsistent with quantum mechanics, the basis for understanding the subatomic world. This has led scientists to seek a more complete theory that unifies these two pillars of physics in a quest to understand the universe. Scientists have discovered anomalies that challenge our generally accepted understanding of gravity. These inconsistencies indicate that our current theories, while robust, may be incomplete. The general theory of relativity proposed by Albert Einstein has become a cornerstone of modern physics. The theory has been remarkably successful in explaining a wide range of phenomena, from the orbits of planets to the behavior of light around massive objects. However, recent research points to possible inconsistencies when the general theory of relativity is applied at cosmic scales. Recent research by Robin Whittle and colleagues in 2024 hypothesized a cosmic anomaly in gravity. Their research suggests that the gravitational constant might not be exactly constant at vast cosmic distances. In particular, gravity appears to be approximately 1% weaker when dealing with distances of billions of light years. This anomaly causes difficulties in understanding what is happening, as it implies a deviation from Einstein's theory on extreme scales. To solve this problem, scientists propose a modification of the standard cosmological model known as lambda-cold dark matter. This adaptation involves adding a new parameter that slightly corrects the gravitational constant on a cosmic scale without affecting its demonstrated precision on smaller scales. The conflict between general relativity and quantum mechanics further complicates our understanding of gravity. General relativity best describes large-scale structures, such as galaxies and black holes, while quantum mechanics provides the best framework for understanding particles at the smallest scales. However, the two theories are fundamentally incompatible. One of the most striking tests of this contradiction is the behavior of black holes. The general theory of relativity predicts the existence of singularities, points of infinite density at the center of black holes. In contrast, quantum mechanics suggests that such infinities cannot exist, indicating the need for a new theory that can unify the two systems. Recent technological advances, such as precise measurements of the cosmic microwave background made by the Planck satellite, have provided new data that confirm and refute existing theories. These observations have led to the discovery of the Hubble tension, a significant discrepancy between the observed and predicted expansion rate of the universe. The Hubble contradiction suggests that either our understanding of the early universe or the nature of dark matter and gravity needs revision. The theory of cosmic failure, which introduces a small change in the gravitational constant, offers a possible solution to this problem. In addition, the detection of gravitational waves by the LIGO and Virgo collaborations has opened new possibilities for testing gravitational theories. These observations provide an opportunity to observe the universe in a new way, potentially revealing deviations from the general theory of relativity that could not be detected before. The intersection of these anomalies with the predictions of quantum mechanics could lead to revolutionary discoveries. Experiments at CERN in the Large Hadron Collider aim to explore the boundaries between these two realms in search of evidence that can bridge the gap between general relativity and quantum mechanics. In the search for understanding gravity, some scientists suggest that it may not be a fundamental force, but rather an emergent phenomenon that arises from deeper principles. This idea does not contradict traditional ideas about gravitation, but opens new avenues of theoretical research. A well-known alternative is modified Newtonian dynamics, or MOND, proposed by Mordechai Milgrom in the early 1980s. The theory suggests that Newton's laws need adjustments at the very low accelerations characteristic of the outskirts of galaxies. According to MOND, these changes can explain the rotation curves observed in galaxies without involving dark matter. MOND has had some success in predicting the behavior of stars and galaxies, where traditional theories of gravity fail. However, it cannot explain phenomena on a large cosmic scale, such as galaxy clusters and the cosmic microwave background, where dark matter is a more acceptable explanation. Another interesting theory is emergent gravity, proposed by Eric Verland in 2010. Verland suggests that gravity is not a fundamental interaction, but arises from thermodynamic principles of information storage on holographic screens. From this perspective, the universe can be described as a hologram in which gravity arises from changes in entropy associated with information stored on these screens. To simplify, imagine the universe as a giant library or a book in which information is stored on shelves with holographic screens. The arrangement and number of books change over time, which affects the overall structure and creates what we consider gravity. Verland's emergent gravity has intriguing implications for our understanding of dark matter. Instead of invisible particles, the effects attributed to dark matter could be a consequence of the emergent properties of spacetime itself. This theory allows us to take a new look at the connection between gravity and thermodynamics. In addition to the theories of Mond and Verland, there are several other alternative approaches. One of these theories is modified gravity, or simply MOG, proposed by John Moffat, which introduces additional gravitational fields to explain the rotation curves of galaxies and the dynamics of galactic clusters without dark matter. MOG suggests that these additional fields modify the force of gravity at different scales. In addition, the concept of entropic gravity, closely related to Verland's ideas, suggests that gravity arises from the tendency of systems to increase entropy. This thermodynamic interpretation is consistent with the principles of statistical mechanics and provides a new lens through which gravitational interactions can be viewed. These alternative theories, although not universally recognized, open up new perspectives for us and require further research and experiments. They force us to reconsider the view of gravity, not as a force inherent in nature, but as a consequence of deeper, fundamental principles. As we move toward the middle of the 21st century, our quest to understand gravity continues to push the boundaries of technology and knowledge. Cutting-edge experiments and missions are being designed to test the limits of our gravitational theories, providing us with new insights and potentially revolutionary discoveries. One of the most important ongoing projects is, of course, the acclaimed James Webb Space Telescope, JWST. Observations to date have been crucial in testing theories of gravity on a large scale, especially those that predict deviations from general relativity. Another key player in gravitational research is the Large Hadron Collider at CERN. This particle accelerator, the largest and most powerful in the world, collides protons at unprecedented energies. These collisions allow physicists to study fundamental particles and forces, including the possible discovery of particles that may mediate the gravitational interaction on a quantum scale. The LHC experiments are fundamental to understanding how gravity can be combined with other fundamental forces. Space missions, such as the LISA Laser Interferometric Space Antenna, are also looming, scheduled for launch in the mid-2030s. LISA will consist of 3 spacecraft that will form a giant triangular interferometer in space. This facility will detect gravitational waves with much greater sensitivity than existing terrestrial detectors, such as LIGO and Virgo. LISA's goal is to observe gravitational waves from the fusion of supermassive black holes, which will test Einstein's general theory of relativity and provide new insights into dark matter and dark energy. But let's get closer to home. The Event Horizon Telescope continues to make revolutionary contributions since 2019. The EHD obtained the first image in history of the black hole M87, demonstrating the power of synchronizing telescopes around the world to create an interferometer the size of a planet. The EHD is now focusing on even more precise observations of black holes, including the one at the center of our galaxy, Sagittarius A star. These observations will test the predictions of the general theory of relativity in extreme gravitational fields. In addition, let us remember the recent study already mentioned by Zhao et al., which proposes a cosmic anomaly in gravity that suggests that the gravitational constant may vary along cosmic distances. This study will be tested with data from the Planck satellite and future experiments on the cosmic microwave background. Upcoming missions, such as the Simons Observatory and CMBS-4, aim to make more accurate measurements of the CMB that may confirm or refute the existence of such an anomaly, offering a deeper understanding of the nature of gravity at the largest scales. In addition, the Vera C. Rubin Observatory, which will soon be fully operational, will conduct the Legacy Survey of Space and Time. This survey will observe billions of galaxies, providing a detailed view of the structure and evolution of the universe. The LSSD data will help test theories about dark matter, dark energy, and gravity, and possibly reveal new phenomena that will change our current understanding. Another exciting frontier is the search for quantum gravity through laboratory experiments. These experiments use highly sensitive equipment to detect tiny gravitational effects at very small dimensions, in which the effects of quantum mechanics become significant. These experiments are designed to bridge general relativity and quantum mechanics, which could lead to a unified theory of gravity. These cutting-edge experiments and missions represent the forefront of gravitational research. They are designed not only to test existing theories, but also to discover new phenomena that could revolutionize our understanding of the universe. Revising our understanding of gravity could have profound implications for cosmology, astrophysics, and technology. The anomalies and alternative theories we have studied suggest that our understanding of gravity is far from complete. As our models improve, we can expect significant advances in several key areas of cosmology. A more accurate model of gravity could solve existing mysteries, such as the nature of dark matter, and the energy we studied suggests that our understanding of gravity is far from complete. As our models improve, we can expect significant advances in several key areas of cosmology. A more accurate model of gravity could solve existing mysteries, such as the nature of dark matter and dark energy. If gravity behaves differently at vast cosmic distances, it could offer a new explanation for the accelerated expansion of the universe and galaxy distribution. This could lead to a unified model of the cosmos that better integrates general relativity with quantum mechanics. For the AST, improved gravitational theories can improve our understanding of black holes, neutron stars, and other extreme environments by accurately describing the behavior of matter under the influence of intense gravitational fields. We can better understand the life cycles of stars and the dynamics within galaxies. This knowledge could even reveal new types of astrophysical phenomena or objects. Technological advances in understanding gravity will certainly drive innovations across various fields. For example, precise measurements of gravitational waves can improve geophysical research and navigation systems. In addition, advances in quantum gravity could lead to new technologies based on the revolution of quantum information and communication, revolutionizing computing and data transmission. Let us imagine a future in which our understanding of gravity allows the development of space-based sensors, leading to new technologies based on quantum information and communication, revolutionizing computing and data transmission. Let us imagine a future in which our understanding of gravity allows ultra-precise space-time sensors, leading to the development of autonomous vehicles, precision agriculture, and disaster prediction systems. As we await the launch of new missions, projects, and discoveries, anticipation grows. Each step forward brings us closer to unraveling the mysteries of the universe, promising a future where our understanding of gravity and the cosmos is richer and deeper than ever.